Good morning, everybody. Should we start? Okay, this is Maprg. We have a 2.5 hour slot and a lot of presentations, so let's start right away. Unfortunately, Dave is not here this time, but I think he might be joining remotely at some point, so we'll see. We have also a note on intellectual property rights in the IETF here, very similar to the note well in the IETF, so you might be familiar with it. In the slides, there are a couple of links to the Jabber room, to the mailing list, and everything you need to know. But given you probably already have found the slides, you might already know where that is. Okay, before we actually start with our agenda, as we usually do, and we have a lot of nice presentations today, I would like to quickly talk about the IAB review we had at the last IETF meeting. So every research group gets reviewed from time to time by the IAB to have some kind of feedback mechanism, discuss how to develop the group and see if it makes sense to continue. We had our very first review with the IAB, and in general this was very positive. So they all kind of liked it, but we also discussed about how to develop the group into certain directions. Because what we do right now, because that's kind of the feedback we got from the beginning from the group, is we focus very much on measurement results, getting people from academia presenting measurement results, and then kind of you can consume this information and talk to the people and get a connection there. So what we do in more detail is that we usually try to solicitate contributions from academia or also industry research. We did so by going to different conferences. Whenever Dave or I happen to be at a conference, we try to announce that Maprg exists and people should send contributions. We also had some lightning talks which were explicitly on the agenda and these kind of things. We create something that we call a call for contributions, which looks a little bit like a call for papers for a conference. And we send this call for contributions not only to our own mailing list, but also to different academia conference mailing lists where usually this call for papers gets announced. And of course, a lot of the presentation you see here is really direct interactions with presentation Dave or I have seen somewhere and we liked a lot and we think it's in scope. So we go and we send those people an email, we talk to them at a conference and ask them to come here if possible. The way we select the contributions is mainly driven really by the charter. So first check is always, is a contribution in charter? And then we also prefer presentations that provide data over presentation that only talk about methodology or something, because that's kind of the feedback I think we got from this group. We, in general, try to fit as much contributions into the agenda as possible, but it's also sometimes a logistic question. So usually we try to prefer in-person presentation over remote presentation, just so that you also have a chance to interact with the speaker after the session or during the whole week. Or sometimes it's just this person can only present at a European meeting or just present at a US meeting, so we have to figure out if we do it this time or next time or whatever. What we really try to avoid is having any presentations in here that are presented in other working groups. That can still be interesting, but usually we have enough presentations, so we think it would be unfair to give time to somebody who already has a slot somewhere else. And we also really prefer presentations which are kind of newish or cannot be discovered somewhere else. Like if there's a video of your presentation, then we might, and we don't have time for you, then we might like maybe decide for a different presentation. What we really liked is that we had a couple of presentations where we kind of scooped the conference itself, so the presentation was before the final presentation at the conference. And then another step we do is that when we have the agenda selected, we try to get slides very early from the presenters, so we can give them feedback and try to guarantee a high quality. And I think actually, and sometimes we give them feedback or request changes or whatever, but it doesn't happen very often, because just like forcing people to send everything early and kind of warning them that you want to like give them feedback or have change requests already kind of gives us a very high quality of presentations. So that's what we do. Any questions on that part? And that's also kind of what we presented to the IAB, and what came out of this meeting was a couple of ideas what we could maybe change or improve. And I want to quickly just like, it's all written on the slides, and maybe you have ideas, or we can also discuss this later, but like give a overview for you. So there was one idea to, instead of having one, so we never requested more than one session, because we thought like 2.5 hours is already a lot, and we don't want to take away more of the IETF meeting time basically. But there was an idea to maybe split up into 2 smaller sessions, so it's easier to deconflict. I've been considering this time, or we both, Dave and I, considered it this time, but it's actually hard because we don't get the contributions very early, so we don't really know how to deconflict, right? At the point of time where the agenda scheduling is done, we don't know that yet. Another question that came up in the review is like, do we actually get the right people in the room, which is like related to the first question, right? Does everybody know if there is a presentation here that is relevant to their own work, that the presentation happens, and do they actually come? We had like, because the room is usually very full, we had a feeling that Maprg is well known, but of course we can do more. We can send like more emails to mailing lists. We could send emails to the chair mailing list, so the chairs can judge if it's relevant for the working group or not. So yeah, any input is welcome here. Aaron.
Is it okay to talk about this now?
Yeah.
Aaron Falk. So one thing I recently did in TAPS was do a reset on the conflict list. And so what you might do is send a message out to the list asking for people who wanted to be here but couldn't because of a conflict. And then you can, you know, maybe get some new entries for your list.
But I guess that depends really on the presentations we have, if you wanted to be here or not, right? Which again is something we don't know by the time where the scheduling is done. Yeah.
There's certainly going to be some people who will only come because of a specific presentation, but I think there are people maybe who are interested in the topic who want to monitor the general effort, but you know, are just in a recurring conflict. That happens you know, from time to time in TAPS.
We can give it a try, definitely. Spencer's in the queue.
You ready for me?
Yes.
I was just going to say that another way to understand what Maria is saying is often in the IETF, we don't know what the agenda is going to look like until 2 weeks, basically until the ID submission cutoff. But here, you guys know what research you've done and what results you've got potentially a long time before, 2 weeks before the IETF meeting. So you might be able to give Maria more of a heads up so that she could not have to struggle so hard with a conflict list.
So Spencer, actually we don't. Like this time we really knew which presentations are in at the time where the draft gender deadline was requested. Because it's maybe we started too late to ask for contributions, but people are also deadline driven, right? Whenever you put a deadline, you get all contributions at the deadline. So, and then like even after the deadline, we were still going to people and trying to talk to them and figure out what they want to present, and there was a lot of forth and back. So it's actually, it would be nice, but it wasn't the case for the last couple of meetings.
I have a dream. Thank you.
Thanks. Colin.
Hi, Colin Perkins. So I don't think this has been a problem, but I think it's something we should look at going forward, is that we're getting increasing amounts of research group measurement research coming into the IETF with things like the ANRW and the ANRP. And we should make sure that there's a clear story for where this research goes and where it's presented. We don't want to be having the same talk several times.
No, so I mean, definitely. So we had actually this case that somebody who presented at the workshop on Monday also a while ago actually submitted a contribution to us, and we knew that this was coming up, and so we didn't have that presentation. So that's something that we definitely try to avoid. How to redirect people to the right group is actually kind of more difficult because not everybody at the workshop is interested in the rest of the IETF, right, in these kind of things. So. Yeah. We also, I mean, it's also like sometimes we have a lot of contributions and sometimes we don't. It really also depends on the location. Like in Europe, we get, for example, a lot of contributions. In Asia, we get less. There are many factors.
Yeah, I mean, this is probably just a case of giving people some guidance for what the venues are in the IETF for this type of work and where they should be thinking.
It's coordination between the different efforts is definitely, but like you can only give guidance as soon as people show up. Another idea that we liked a lot, and Dave might proceed a little bit more, is to organize a measurement-related hackathon session. We don't know what that means yet, if we just say, like, if you want to do something on measurement, come to this table, or if we actually think about, like, very specific project where we say, like, we want to hack on this measurement tool, we want to run, like, this kind of small measurement study today, and then see if people are interested. So if you're interested in contributing to that part, or you have ideas what you would like to do at the hackathon, please talk to us. Another thing that was discussed was, and that was discussed in this working group at the very beginning, is how do we get actually hands on the data? How can we make sure that all the data that is presented is available for further research and analysis? And how can we support this kind of data exchange as this group? I think that was kind of also the main motivation why we started this whole effort at the very beginning, but like we very quickly understood that getting data at hand is also not easy in a lot of cases. And we had the feeling that people are happy with kind of getting these presentations and then getting directly with those people in touch and see if they can do something further. But of course, we could also do a little bit more effort and try to figure out, like put in the wiki, for example, where this data is available, which data, or let everybody who presents fill out a template and tell us about the data, what kind of data do you have, what format, how much data, where to find it, these kind of things. Would there be interest in this kind of effort? Nobody at the mic, but you can send me an email if you want. Then another point that came up was like, do we want to connect? Do we want to use this group to connect to the operators community? And there is a group at the RIPE meeting, for example, that's called MET, that's also focused on measurements. So we could try to like more closely work with them together. But I have to say, like, I'm actually not certain about that point, because first of all, our charter says we're targeted for IETF meetings. And second is, given we have this mode where we kind of present data, I don't think there's something where you can like do a lot of common work, because it's just a forum for discussion. Brian, who's the MET chair.
Hi, Brian Dremel, right at WG co-chair. Yeah, I think that's probably the right way to do it. I mean, like, you know, we talk occasionally, you and I, and the meeting cycles don't line up, you know, in such a way that there's much conflict. So, yeah, if there's stuff that's here that I think should also go to RIPE, I will approach people, and you know, vice versa. So I think that there's, you know, a lot of the stuff that's here is, I mean, they're slightly different focuses, right? Like, so the MAT stuff is things that are meant to be a little bit more operationally relevant, but also things that are sort of, you know, even just interesting. So yeah, I have, one of the reasons I'm here and I cover this is looking for interesting things to encourage to come to MAT. So.
Yeah, so I mean, like, this one is easy because you're sitting in the same office, but maybe there are other groups that are focused on measurements and I'm not aware of. So if you like involved or you know of these groups, let me know. We can see if that makes sense to cooperate. And then a very last point was also that like some of these presentations might be interesting for an IETF blog post. So in general, we see like more posts on the IETF blog. And I already did this and talked to some of the people who presented the last time, and they will write a blog post. So if you are presenting or you have some data that you think is interesting and you would like to write a blog post, just come to me.
And if you write a blog post, you get a free t-shirt.
Oh, didn't know that. Ooh. Okay, any comments, further ideas, discussions? No, you're all waiting for the presentations. Okay. That's the agenda for today. So we have 2 head-up talks. Both are more focused on tools and methodologies and on measurement data. That's why they're head-up talks, because as I said earlier, we are like trying to focus more on the actual data. And then we have 6 talks all over the place. So it's about privacy, IPv6, DNS, packet sizes, so the typical stuff we are interested in. So let's start. Giovanni, where are you? There. You want to try, wait, is that connected? Yes.
Yeah. So good morning, everybody. So this is a heads-up talk. It's just a 5-minute one. This is a paper we have presented at TMA conference in Vienna. It's a tool and allows you to automate measurements related to domain names. So one situation we face as SIDN, it is like if you wanted to measure a lot of properties associated to a domain name, let's say wikipedia.org, if you want to know stuff like where the DNS services are located, information about SMTP, HTTP, where it's hosted, it's very hard to do that with current tools. There's a bunch of open data sets, but currently there's no tool that do that automatically for you. So if you want to measure all these different protocols associated with any domain name, we would end up to have something like that. You have to use ZMap, Dig, Mascan, a bunch of other tools. You can do it, but it ain't pretty, and that's a problem because you end up wasting a lot of time doing repetitive tasks. You have to deal with very different data formats. You waste, again, a lot of time. More complexity, as we know, leads to more errors. And it's very hard, as if you're an academic reviewer, to review papers and try to reproduce those studies because you're going to be wasting a lot of time in just doing the measurements. So what we decided to do is to build a new tool. It's called DMAP, Domain Name Ecosystem Mapper. And what it does is just automate the measurements of 5 protocols and also take a screenshot of a domain name of a website if it exists. And the way it works is different from ZMap. ZMap, usually you have a list of IP addresses already just generated for you, but this one you have to provide a CSV with a list of domain names. It can be its own files we use for .nl, which is almost 6 million domain names. And in a single machine, we do 1 million domains a day, but this application is also distributed, so you can scale up very quickly and easily. This is the website. Let me see. There's a bunch of stuff in the paper, applications, demos, whatever, and SQL code to analyze that. Oh yeah, the good thing about this tool is that later, once the tool does all the measurements, it's very easy for a researcher just to analyze the results using SQL. So we have a demo data set on the website, it's Alexa 1 million. The queries are there, you can download it, analyze. And I just want to show one thing. This is a table that shows the various properties that we have measured using Alexa. And one thing we found is that currently on Alexa 1 million, 77% of all the domains support HTTPS, and 1 in 5 are using Let's Encrypt. There are many more findings in the paper. Just would like to encourage you to download. The only thing we make is like we make it only open source for researchers because this has some kind of a commercial application possibility, so we just don't want to incentivize that. So just click on it to have to register. We're going to give you the access to the repository and GitHub, and that's it. Thank you very much.
What? We actually ahead of schedule, so there could be questions.
Oh, yeah.
But I guess we just move on. I have to leave the mic here.
Yeah.
Okay. So I'm going to give you a key overview about monitoring DNS with open source solutions. This was presented on the SRE Connect in American. Well, so DNS is currently monitored in two different ways. One is doing a pre-data aggregation, and that is done by aggregating all the information onto the DNS server and then sending it to a central server for the visualization. This method is used, for example, like DSC that was developed by ORG, and we also have DNS data that is used by the root servers. The second method is doing the disaggregating data, sending and storing it, like storing the route package of the DNS. This method is used by Entrada, for example, that use a Hadoop cluster to process and store all the information. Now, the problem with this method is that it doesn't give too much information about the current status of the DNS server. So we started looking about how we could improve the current methods. And for this, we first tried to develop our own solution. We developed Rata DNS that did the capture, storage, and visualization of all the data. But we saw that we were reinventing the wheel. Many of the things that we were developing were already done by someone else. And also, when we presented this to the DNS administration, they found that it was like too wide. They didn't like it. So we started looking to open source solutions. We saw that many of the problems that we were presenting were already done by someone, were already done in production. And we started analyzing different software for the capture, storage, and visualization. For the capture, we compared different software like Packetbit, Collective, DSC, and we saw that many of them didn't support all the transport or network protocols that DNS use. So in this case, we had to develop our own solution that was DNS Zeppelin, which captured all the information and sent them to a central database for the processing. We also compare and did a benchmark of the different storage, like Prometheus, Druid, ClickHouse, InfluxDB, Elasticsearch, and TSDB. And we also compared the different visualization softwares. Finally, we end up with an architecture like this, where we had the DNS servers and we captured all the information with our own solution that was DNS Zeppelin. All the information was sent to a ClickHouse cluster, and finally, it was presented in a Grafana visualization. The result was something like this, where we have, for example, top query domains. That's some information that was never analyzed directly in real time. We also have the unique domains names that are query per second, for example, the average packet size and the total packet size. We also have some general information like the query type, query class, and everything that the other software already provide. Some of the performance on the single server setup, we tested with real data from the NIC Chile. We found that we could process like 7,000 packets per second. And we found that it used 34 gigabytes of data, and we could store that in 4.7 gigabytes every day. So it's entirely possible to running like and store like a year of data or more. We also tried to flood our own servers. It was a pretty fun experiment, and we found that we can handle like 120,000 packets per second on one single server, and the database never go up or more than 30% of the CPU. And this was like a 2-core computer, so it can scale a lot more. So this is what the presentation about my tool and when monitoring DNS servers. Thanks.
Thank you. Any quick questions? Yeah, somebody coming. Okay.
Yes.
John Reed, Akamai. Sorry, maybe I missed where you were capturing packets from recursives, from authoritatives, from both? Where?
It was the authoritative DNS servers of Chile, the CCTLD of .cl.
The authoritative end.
Hmm?
So the authoritative servers.
Yeah.
Okay. Yeah. Did you consider or have any insight in gathering data from recursive servers? I know one of the challenges is we can monitor what the authoritatives are giving back. That doesn't tell us anything about the end user experience.
You can monitor whatever you want. We only capture directly from the wire the package,
Right.
so you can store anything, whatever you want.
Okay.
Sarah Dickinson, could you say a little bit more about the format you're using to capture the data? Are you capturing full PCAPs or a reduced set of data?
what we capture is the entire data, the entire package, and we just extract what we need. For example, we extract the domain name for querying, the type, class, and that is what we store in the ClickHouse database.
Because there is a draft going through DNS op at the moment, which defines a DNS-specific capture format using CBOR.
Yeah.
And I don't know if you're doing something similar or you decided not to use that for a specific
For
reason.
now, we don't use that format because it was like very early into the draft when we developed this tool. Well, with this architecture, you can actually swap, for example, the capture process and you store directly into the ClickHouse database, and you can also use that. It's not a problem.
Okay, all right, thanks very much.
Okay, thank you. Thank you. Ian?
I have some recent data on UDP packet reordering that we're seeing in Quick. So obviously I can't say whether this is representative of what someone else might see. I can't say it's representative of TCP, but at least for this data set, it's fairly representative. It wasn't Chrome stable, so we're talking fairly large sample sizes. Millions of users and many servers. And we have some from the server side and some from the client side. The core metric is actually exactly the same, and the measurement code is exactly the same. But it turns out the data does end up displaying a little bit differently, and I apologize for that. That difference makes it a little bit more difficult to interpret, but we'll walk through it anyway. Sorry, I probably should have just gone to this slide. Also, we're using BBR congestion control on the server side from server to client, but we are using Cubic from client to server. So that actually may affect the measurement data. It may potentially change the likelihood of reordering. Also, the client side data, which is, so client is the client receiving and it's measuring on the receive side, and the server is sending. So those flows tend to be longer. They're CDN flows in this particular case, like large video playbacks, things like that. The server side data tends to be, obviously less data intensive with a few exceptions. So there's an inherent asymmetry, at least in this, but it kind of reflects typical web traffic. So hopefully it's informative. So the first fact is just how many what percent of connections have at least one reordered packet. On the client side, it's only 5.4%. On the server, it's 9.4%. I can't really explain why there would be more reordering going upstream than downstream personally. Maybe someone else can. Could be Wi-Fi, because we can blame everything on Wi-Fi. But a big takeaway is, 90% of connections see like no reordering whatsoever, right? So like if you're trying to optimize your loss recovery, like maybe we should be optimizing like, for the like 90% first and then like ratchet up. So certainly I didn't expect it to be quite this stark, but this might be even more motivation for like a more adaptive scheme. And it certainly is motivation that like the approximate scheme rack has chosen, where initially it uses packet number threshold and then drops over to time-based is pretty compelling. So the remaining data excludes connections with no reordering, because I don't really want to look at a bunch of like percentiles where everything's 0. So this is on the client side. So on Chrome, Chrome is receiving packets. And this is in packet number space. And this is actually pretty brutal and depressing. So I had to put the bottom scale at a log scale, because there's still like a decent amount of energy around 100. And 1,000, I mean, I think we don't actually get to like under 0.1% until like a few hundred. So things are pretty bad in a packet number space. And in particular, as you can see, 10 is like a few percent right there. So the default reordering threshold of 3 is kind of woefully insufficient for something like half the time when reordering actually does happen. So it's sort of, you pick a number and you go with it, but it's sort of a weird number. Things look a little bit, do you have a question? Sorry.
Tommy Polyapple, just clarifying question. On this last one, so this is of things that were reordered?
Yes, so this means
is this both directions or?
This is only on the client side, so I'll go to the server side
Okay.
data after. I'm going to do all the client side data and then all the server side data. And I think this metric, I can't remember if I have this metric on the server side or not. Yes. So on the client side, we also happen to record it as a fraction of min RTT. So that's just kind of an indication of like if I was to do it in a time domain, what would it look like? And here it looks quite a bit nicer. So you see, there's almost no energy before 25%, or sorry, after 25%, except for that blip at the very end, which this is running in user space. So I'm going to suspect that that's Chrome basically hanging for some long period of time and thread jank or something like that. So yeah, so this looks quite nice. Like there's very little energy even past 12.5%. So we're doing much better. I did have to filter the min RTT to greater than 100 milliseconds to get this data to be like sensible. It turns out that there are some clients that measure like sub-millisecond RTTs, and obviously if you have a sub-millisecond RTT, your fraction of min RTT just kind of goes crazy. It'd be interesting to get data for like greater than 10 milliseconds as well, which kind of is a more sensible thing. So the fact that it was so crazy though is probably motivation that we need a min. Like if you're gonna start using time-based loss detection, like probably you need something that's on the order of like your clock granularity or your timer granularity, like 1 millisecond, some amount of minimum threshold just to kind of ensure some basic sanity in the network. To do.
Yeah, Aaron Falk. I'm finding it hard to get at the intuition around this without having some understanding of how distributed this is over flows. Like, do you have like one flow that has a lot of problems, or is it kind of spread out? And same thing for paths, same things,
Yeah, on the server side, I have the number of packets, I think, reordered per flow as well. We'll get to that later. I don't have that on the client side. So this is the max time for a given flow. So this is not even the typical time, but this is an effort of saying if I had an adaptive kind of time-based loss detection that like ratcheted up the time threshold to whatever was necessary to never spuriously retransmit a packet, kind of how much time of reordering window would I need to make that happen? That's my internal logic.
Yeah, I guess it's just like when you the PDFs that you were showing before, when you're showing like numbers of events that you're measuring, do you have like a single flow has this multiple times, or a single path has it multiple times? I'm just trying to understand how pervasive are the statistics.
Like, is this a one-off event, or is it like?
Is it localized? Is it clustered together topologically?
I can't give you good information on that. I can give you some kind of knowledge from my experience with looking at packet traces, which is having like one packet race in front of a bunch of other packets is oddly common. So I've observed that a fair amount for UDP. I don't know if that's a common thing with TCP. And I assume it's a matter of you overflow like one buffer on a switch or something, and switches are heavily multi-threaded, and you pop onto the other one and it has no queue. Something like that. I'm not exactly sure. So that phenomenon is common, but I can't kind of give you any more prevalence data than that. I know. On the server side, here's the number that does actually give you a prevalence number. So we don't have this on the client side. This is for connections that have reordering, how many were reordered. And so it looks like, in this case, there's a lot of energy, around like in the sub 80 region. That kind of makes sense. I mean, most of these flows are fairly short. And one fun fact is, 38% only had one packet out of order on the server side. So that would say it's fairly rare overall in the scheme of things. Here's it in percent. So again, it's fairly rare, but the distribution's a little bit shifted. As I said, a lot of these flows are quite short on the server side. So here's the kind of same thing, like the maximum gap in quick packet number. Here's the number that we were looking before on the client side. Unfortunately, this is inverted distribution, so I have to kind of translate. But as you can see, the first kind of big plateau is 1. So over 40% of packets were just like twiddles, as they are sometimes referred to as. And then you get a fair amount of energy around 2 and 3. And then, you know, kind of things go off the chart on the top end from there. So it seems on the server side, the maximum distance in packet number is smaller. I think that's mostly a product of the fact that usually we have a smaller congestion window going from client to server than from server to client. I don't think it's, I could be wrong, but I don't think it's actually an inherent network property, unfortunately. If we look at the same data, fraction of min RTT, when your min RTT is greater than 100 milliseconds, should have swapped these graphs around, but it looks pretty similar to the client side. It's pretty heavily distributed towards, you know, like under a quarter of a min RTT. So the vast majority of connections see no reordering. The tail is very, very long. In packet number space, it's depressingly long. Quick runs in user space, so you know, small amounts of network reordering may occasionally get amplified into much larger amounts of network reordering due to like thread jank, particularly true on the client side. And so hopefully TCP actually might see a little bit less reordering if things are going well. The 1/4 RTT reordering threshold that is currently recommended in the quick recovery draft actually seems pretty sensible after looking at this data. And it certainly seems like this is motivation for like an adaptive scheme, because it seems like the vast majority of connections could get away with a very, very short reordering tolerance that maybe handled twiddles and nothing else initially, and then ratcheted it up to something more aggressive later. At least those are my thoughts, but questions, comments?
Eric Nygren, do you have a sense of what fraction of this of these are fragmented packets, and whether fragmented packet reassembly might be leading to any of this?
So we set the do not fragment bit, at least on the server side, and I believe on all client side platforms that permit it, which is not, at some point it wasn't Mac, but I don't know why. Anyway, yeah. So hopefully we're not getting fragments. I mean, the network does weird things.
Hi, Colin Perkins. So I was actually surprised at how much reordering you were seeing. I was expecting the numbers to be a lot less than this. You said at the beginning that you blame Wi-Fi, and I suspect that's probably the case, but do you know that, or is that an assumption?
I do not know that. I mean, it's very difficult for me to piece things apart exactly like where these things happen, fortunately.
Sure, okay. I guess my other question is, do you have any insight into whether there are patterns of where in the connection the reordering happens? So is it always the first packet getting delayed, for example, or something like that?
Based on looking at traces, the patterns that I see here is, one is this, like, you get this small packet that races ahead of large packets. That tends to happen at the tail of a response. So you get this long, so it happens when two things happen. When you build up queue pressure and then you send a small packet. So that combination, some portions of the internet seem to decide that that's a thing they should race ahead. And so, you know, if you don't have any queue pressure, then the small packet doesn't need to race ahead of anything. But like if you kind of, you know, produced a few milliseconds of buffer bloat, then it'll sometimes race ahead.
Yeah, okay. But you're not seeing, for example, the first packet in a flow being delayed because it's
I haven't seen that.
Or something like that.
I've heard that is a potential, is it like 3G issue or something like that, where the radio is firing up and maybe that's happening?
Yeah, okay. I mean, that's good for connection establishment if that's not happening, so that's a good.
Yeah, I see very little reordering in connection establishment, typically.
Thank you.
At least in my anecdote. Yeah.
Hi, Brian Trammell. Anecdotally, we would also blame Wi-Fi. I mean, so where we've done stuff like in the lab where we're looking at different connection things, it's always like the dodgy little wireless router thing, and they suck if you come over the wired interface, but they suck a lot if you go over the wireless interface. So you know, we have like 1 or 2 boxes that we've done. I mean, we weren't actually looking at reordering, we were looking at something else, and reordering messed up our stuff, right? And it was primarily on those boxes. So yeah, let's blame Wi-Fi.
Yeah. Okay, great. Well, thanks. Oh, do you have a question?
Gory Fairhurst, thank you. It's fun to have real reordering information. I wonder whether this is partly a function of what you measured. The fact I see TCP maybe having less reordering, maybe it's the function of your congestion controller actually pushing hard for a little while. So I wonder whether as a community, we could kind of gather more stuff. And do you think that would be useful to kind of look at other transports, other links, and see what we can actually derive from this?
Yeah. I mean, I would love to see exactly comparative data for TCP in particular. It might be very difficult to actually gather due to GRO and various other kernel things that are helping us out. But yeah, it'd be incredibly interesting.
Yeah, I didn't say it was easy. I said it was interesting.
I mean, Google is still doing using TCP, right? So eventually can come back with TCP data at some point.
Yeah, maybe you should ask Neil and Yucheng about that. I don't know if they're.
I will back them up.
But yeah, maybe it might actually be possible. I can try to see if I can coordinate with the teams.
That would be great. Okay, thank you. Please leave the clicker.
You want that back?
Right. Yeah.
Good morning, everyone. Hi, I'm Brian Trammell, ETH. This is work I actually did with Miria, but she's chairing, so I'll present. And we ask a very simple question, and we have a very simple answer. Is buffer bloat a privacy issue? Actually, I want to see, is buffer bloat a privacy issue, yes or no? So hands up for yes. Yeah, hands up for no. Oh, yes. Buffer bloat has a potential privacy impact. Okay, that's interesting. But there's a big asterisk on this. Yes, everything's a privacy issue, right? So if you have significant buffering on a link, right? So yeah, that's buffer bloat. If you have a public IP address that is associated only with that link, if the public IP address responds to an ICMP echo request and that echo request and reply share the buffered queue, then I can ping you and figure out how big your queue is. This is very surprising to me. So I decided to come and talk about it. For networks that we examined, this is I would almost call this anecdata. This is a extremely biased study of people that I could get to click on a link in a tweet. But for 1 in 7 of the networks, these conditions hold. So this is actually, advice we've been giving in the transport area for a long time is like fix buffer bloat, but now we can say actually, no, seriously fix buffer bloat because this is a problem. How did we get here? This is sort of a recap. I didn't actually set off to try and answer this question. I tried to answer a completely different question. So this was, this is the quick portion of the morning, I guess. So this was a question that was sent to the quick RTT design team in the spin-bit discussions. Is RTT data privacy sensitive, passive RTT data privacy sensitive? And the idea is, yeah, if I can ping you, I can know where you are, not what you're doing. And, you essentially do very simple trilateration. You basically take the radius is equal to the time on each of these pings, multiply it by the speed of light in the internet, run, do some very basic math. Actually, it turns out that the data is usually fuzzy enough that when you do this very basic math, you divide by 0 somewhere. And if you're not dealing with complex numbers, bad things happen. Usually this is done in a more approximate way, right? Like, so these are the RTTs by color. So green is faster to a particular anchor in the RIPE Atlas network, which if you just look at the colors, you'll guess it's kind of, yeah, it's probably there in Europe, right? And you'd be right, yes, it is indeed in Europe. When we looked at this, we actually found the internet RTT is the sum of delays at each hop. A lot of these are variable. You can only derive distance when your queuing, stack, and application delay are held to 0, which basically never happens. The network operations rule of thumb that 1 millisecond of RTT is a little bit less than 100 kilometers at distance holds. So if you know the IP addresses, then trying to do geolocation by exclusion based on RTT data is somewhat more erroneous than even the cheapest, lowest quality IP geolocation database, right? If your RTTs are over 10 milliseconds, which doesn't happen in the internet all that often, then you're getting at best exclusion information for national level, right? So this isn't a problem. But we were concerned in general about the geo-privacy implications of passive observation of RTT. Turns out to be not that scary because of all of this variation. But then we flip this question around. Does active observation of RTT pose a problem? And this is one of these things where we're actually just sort of like cleaning up the, we were writing a paper on this and we were sort of cleaning up the, you know, looking at all the loose ends, you know, we're actually going to get this question. So let's actually go ask that question. And we asked the question about remote load telemetry kind of as an afterthought, right? Can a remote entity armed only with ping get information about the operation of machines on my network? So, you know, this is me, this is the internet. And here, if we look at the, you know, the equations before about how we actually, what these components of RTT do, then the load on the network is equal to the sum of the queuing delay in one direction and the sum of the queuing delay in the other direction. If I have a cheap router and somebody's going to ping me from very far away, can I actually get information? So what I did is I set stuff up on my cheap router and I started downloading the kernel from somewhere, and then I pinged myself from Singapore and Amsterdam, and I got this. That trough to peak, so that's like basically 0. It turns out I'm in Zurich, which is not that far from Amsterdam. This is Singapore, which is about 220 milliseconds. It's a little bit further away. When I was pinging myself here like, you know, about 10 times a second. And when I started downloading stuff at full rate, you know, boom, I see this peak of 800 milliseconds. I'm like, wow, okay, I'm an internet measurement researcher. I probably should have noticed that I have a second of buffer bloat in my own network, and I hadn't before that. And I was kind of like, wow, that's scary. And then I went down here and I actually started using rate limiters to limit the rate to other than full rate. Let's not fill up the entire pipe. And I was even able to actually see some variance here when I was pulling down 300 kilobits a second on or 300 kilobytes a second on a 40 megabit link, right? So even if I'm only at 10%, I can actually, you know, that signal looks different than that signal looks different than that signal. Can actually estimate the rate across there. So my connection sucks, good. How widespread is this phenomenon? So we stood up a piece of software that if you go and you click on that link right now, you're probably going to cause it to fall over because I've never actually had a room this big go and click on it. So feel free. It actually kind of does work. I'll warn you that JavaScript was me learning JavaScript over Christmas vacation. So you might get in a situation where you give me data and I don't show you the graph. If it fails and says that I can't ping you, send back the link to me and I can give you your data if you're interested. The way that this works is that, you know, I have a ping server somewhere. The client side JavaScript sends a ping request. The ping server starts pinging. Then after delay, I start downloading. Actually, I think I start downloading the Hubble deep field from a CDN somewhere. I keep pinging, and then, you know, the ping server itself keeps the ping information. It'll only actually ping the public IP address from where the request comes from because you don't want to turn this into essentially a botnet. And I left this up and, you know, kept this running and updated stuff from just before I left for Montreal. We ended up with 106 measurements from 66 different networks. 33% of these networks always block ICMP. And, you know, so 7/8 of definitely mobile networks. So basically we classified these by autonomous system number to see, are you an access network? Are you a, you know, are you a terrestrial access network or a mobile access network? See a lot more ICMP blocking in mobile access networks because there's, you know, generally some sort of NAT somewhere along the path. On 33% of these networks, there's no indication of load dependent RTT, which means that last mile segment is either, there's actually NAT, so you're hitting a thing that is not the congested queue on the way down, there's a queue in the way, or the queues are tuned in such a way that you don't actually have buffer bloat. And we're into remote load telemetry, which might work on about 14% of these networks. So, you know, what this looks like, so, you know, we start pinging here, we stop pinging there. This is one Swiss access network, and you see here, even though you have a public IP that's pingable at that point in time, you see no variance. This is what happens when you do it on my network. So because of how the pinging works, we don't fill the queue all the way to the top. It's not maximum load. I'm only seeing 300 milliseconds of variance there as opposed to 800 milliseconds. And this is a very easy signal to sort of see. So coming out of that, you know, recommendations for protocol design. remote load telemetry. Anyone who can ping you from anywhere on the internet can measure your network activity. I will leave why this might be a thing that you don't want as an exercise to you, the audience. And you can take away sort of like 2 bits of advice here. Some of it is good advice and some of it is bad advice. And it seems that there's evidence that both bits of advice are being followed in various places, right? Like, so 2 ways to fix this. You can debloat all the buffers and deploy AQM and ECN. That will fix it, right? And there's, at least anecdotally, one of those lines where everything is good, that's how they fixed it, right? Like, because I know the guy who built the network. Bad advice, you could also just roll out CGN everywhere and block ICMP. That would also fix this. And other forces are causing that to happen as well. So with that, I'm done and we'll take questions. How much time do I have?
So I'm struggling with your initial premise because I believe the only private information that this exposes is that you have a crappy router. And
well, I mean, if you ping me over time at a rate that I'm not going to notice, you can tell when I'm using the network versus not using the network. And if we go back here, if you ping me faster than I was willing to ping with this hack, the pattern of I'm doing a bulk download looks somewhat different than the pattern of I'm doing adaptive bitrate multi-streaming. So there's a difference between web and Netflix and chill on this graph. Now in this case, this was 10 pings a second. So if I had a competent network in front of me, they would probably actually report that as abuse. But I also have 800 milliseconds of buffering on my cable modem. So I'm not sure I have a competent network in front of me.
all right.
I was able to do this to myself for a long period of time and nobody noticed.
I believe you can do it. I guess I'm just insufficiently paranoid to consider that private information.
Okay. What's your IP address at home, Aaron? Oh, okay.
Why do you need the ICMP echo? Why not just sending TCP SYN and waiting for the reset?
I could also do that. The reason that I did ICMP is because I was using ICMP in the rest of the study, and I wanted to compare ICMP to ICMP, ICMP to ICMP. Another reason not to do, I mean, so if ICMP is blocked, you can use TCP, SYN and reset. No, you get SYN and then you get a reset if there's no server. Yeah, right. The TCP SYN to reset gives you the I mean, really, the short answer is I was lazy. Ping was already in the environment, and I wanted data that was comparable to the rest of the study for the paper.
Yeah, Giovanni Sadian. Yeah, thanks for the presentation. Coming back to the ping thing, I think that Stefan just said, the good thing about ping is just like it's less blocked in other applications as well, it's less invasive. So there's the good side of it. The bad side is many networks treat pings differently. They put like in
right, exactly.
So I was wondering how that impacted your results.
So it might be that some of these networks where there's no indication of load dependent RTT is because the ping packets go through the same queue assumption doesn't hold. And actually, I'm gonna take Stefan's idea and actually hack up the tooling to be able to do the SYN RCT hack as well, because that should go through the same queue in ways that ICMP won't. And if I rerun that on the networks that I already have information on, then that could, I could see if I can get any out of that no indication of load dependent RTT space. So thanks, that's good advice.
Wes Hardiker, ISI. With respect to the privacy problem, so in NDSS, the DNS workshop this year, I showed that just by studying DNS packets leaving my house, I could determine things like sleep-wake cycles and stuff like that. So this sort of actually augments that even further because, you know, certainly we all stream Netflix starting at 8 p.m. at night, and that's when we watch most of our bandwidth, and we'll notice when you're not at home and things like that, and when you're at work, and those do become important.
Yeah, so the thing that kind of struck me about this is that the DNS stuff requires you to be somewhere on the path between the network and its first recursive resolver, right? Like, so you need some passive measurement here.
Yeah, specifically, I studied it from the point of view of an authoritative server. So actually, just looking at stuff.
Oh, okay. Yep.
If I was just .com, for example, I could determine your wake cycles.
Right. But I was able to run this just by renting a cloud server and pinging people. So
Hey, Benjamin Dam, I just wanted to say I really appreciated the research. I think it's very insightful. And I'm reminded of the adage that if you haven't got anything to hide, that's because nobody's trying to hurt you.
Yeah, think about this. You can also like use this to monitor, for example, different websites and the load they receive, and get like a lot more information, not only for personal information and like, for example, corporate information. How many people are visiting your site, when they're visiting.
Lorenzo Culiti, I mean, you had good advice and bad advice. There's sort of like partially bad advice as well, which would be sort of randomized delays on ICMP responses.
Yep.
Something like that.
Right. That would break
Probably
ICMP
more
for
bad
what it's
than
for.
good.
Yeah. I'm gonna put that in. I'm gonna put that straight up in the bad advice column.
Thank you.
All right. Thank you very much.
Kieran is next. So Kieran presented already at the NR, NRNW workshop on Monday. So you might have seen him already, and he's here the whole week. So we took the opportunity to ask him also to present some of his other work in this meeting.
Thank you, Mirja. Hi, everyone. I'm Kieran Scheitle. I'm a PhD candidate at Technical University of Munich, and I'll talk about a quite specific and quite technical topic today, which is de-aliasing IPv6 hit lists, and I'll briefly get into what precisely that even means. It's based on 2 papers that I'm listing for completeness, so if you want the background, go to these and have a look. And of course, it's, as everything academic, it's joint work with Oliver, Minu, Georg, Pavel, Kasim, Maciej, Stephen, Luke, and Georg again. So I do a lot of security scanning in the internet, and in IPv4 that has become fairly easy recently because you can simply ping all the addresses. In IPv6 that doesn't work, the address space is just too large. So we are back to using hit lists, what we did for IPv4 10 years ago. To have these hit lists, there's basically 2 approaches. One is, first you need to collect addresses from whatever source you can get, DNS, passive observations, whatever. And there's also some papers that then use these lists to generate more addresses, like learn the structure of IPs in those lists and generate new IPs and see if they respond. And there's plenty of related work going on, so I'm really not the only one doing something in that space. And the question that struck us is, are these lists biased? So are they biased towards certain ASs and prefixes, which means they would not give you a representative sample of the IPv6 internet? And this is really enlarged by the problem that a single host in IPv6 can bind billions of IP addresses to itself. So you can bind entire prefixes to one single host. And if you run into such an area in your hit list, you will definitely have a strong bias because you will count a single machine billions of times. We call this aliases because it's one IP address or many IP addresses and just one host for which you have many aliased addresses. So you can call it an alias prefix if all the IPs in that prefix belong to the same host. So just a brief intro. So this is what our current IPv6 hit list looks like. It's also published, so if you want IP addresses, they are there. It consists of many components like domain lists in DNS, domain lists from certificate transparency, but also, for example, running trace routes to all the IPs and finding router IPs in between. So that's just a brief overview. We have around 50 to 60 million of IP addresses. The question is how many of these are real and not just aliases. So the state of the art in detecting aliases is basically saying, I'll take this prefix and I will send probes to certain IP addresses. They can be random or they can be fixed, whatever you prefer. And then if I get a certain number of replies, I say it's unlikely that some random IP will just respond. So I assume this is aliased. And state of the art is somewhat that typically you only require a subset of IPs to actually reply. So let's say 3 out of 8 or something. It's also typically done at a specific prefix length, like /69 or whatever. And the issue I had with that is that if you use random addresses, your targets may actually cluster. So a random process typically doesn't give you nice distributions, but you can have clusters, which you wanted to avoid. If you use fixed addresses, you get a nice spread, but people may predict those addresses, and also they may be in use, because if they stand out to you, they may also stand out to others. So what we said let's do is we said let's combine these two approaches. So basically, we enumerate all the combinations for the next nibble, and then add a random portion. So for each prefix where we say this might be an alias prefix, we send 16 probes, and they are reasonably well distributed, but not predictable. And we do that at many levels, and we also probe ICMP and TCP-AD. So some parameters that we used in this. When do we suspect something aliased? It's if we find more than 100 IP addresses in some level of the prefix tree. Then we say, let's run this alias detection on this prefix. Then, of course, we said we want all the IPs to respond, but of course there's packet loss. So what we did is we said if an IP replies on either ICMP or TCP, we'll accept that. And also we have a sliding window of past measurements where we also accept replies. And that works really well to really increase the bar to say all the IPs must reply. So we have very few prefixes where we have 15 or 14 replies or so. Typically it's either all or none of these random IPs that reply. And one very interesting impact that we did find is that we would actually find prefixes that appear to be aliased at a high level, like a /32 level, but then you could find tiny pieces in it that would not be aliased, where IPs would not reply. And this is a quite interesting phenomenon. So typically it might be that some portion is routed differently, like the all zeros address being used for routers or something. And hence we can't simply build a blacklist, but we actually build a multi-level prefix tree and do longest prefix matching in that to say which portions are aliased and which are not, and to also have it not cover the full length under an alias prefix. Yes, that always takes a time to render. So what's the result? Basically, we had these 55 million IP addresses, and almost half of these addresses were in alias prefixes. And if we do this plot, which we did using sesplot, which was presented at last Maprg by Luke, then you find it's very few prefixes, and these make up a lot of addresses in this list. So this is, if you think about it, as expected, but it's still quite alarming that half of the hit list is basically just double counting one IP address or one host. So to us, it was quite surprising that it's actually half of these addresses that are basically aliased. If you look into what are these prefixes, it's typically, there's a wide range, but a lot of them are Cloudflare, AWS, or something like that. And we know they sometimes use tricks like having basically a packet filter on random IP addresses that were forwarded. But still, you shouldn't be scanning and double counting these IP addresses. Good, then the next thing we did is, let's do some validation. We have this technique that claims to find alias prefixes. How can we increase our confidence that this actually does what it's supposed to do? So here we did use advanced fingerprinting, which we have used earlier to detect cases where an IPv4 and an IPv6 address belong to the same host. So you can use certain features to increase this confidence that it's really the same machine you're talking to on this set of IP addresses. Some of them are good in confirming this, some are good in falsifying that. It's not always that black or white. For example, you can look at the initial TTL that you get back, and it doesn't really mean something if it's the same, but it means a lot if it's different, because then it's quite unlikely that it's the same machine. You can also look at TCP options fingerprint, like the order, the padding, these small details in TCP options replies, and also into TCP timestamps, which can be linear if you probe a lot of IPs in a prefix in a certain time order, and you get a linear TCP timestamp over all these packets. You can pretty much assume it's the same counter behind all these IPs, so the same machine. And what's important here to mention is typically you could say just use Nmap, fingerprinting, whatever, but we need this to scale. So all these methods work with just 1 or 2 packets that we use for liveness probing, and we just extract more data from that. So it comes for free on top of our measurements. If we look at what we find, we fingerprinted these 20K prefixes that we considered aliased. Here we just do it at a /64 level, so we have a somewhat stable set to look at. And the confidence, of course, depends a lot on the test, what I just say. So if it's the same ITTL, it doesn't mean a lot, but if it's different, it does. And of these 20K, basically we find 1,000 or so where we say, this looks odd, it looks like it's not the same machine, it displays some different behavior. But we also find 13,000 where we say even the timestamps behave linearly, which is very unlikely if you would probe different machines that they randomly pick the same TCP timestamp value over time. So for us, this was a confirmation that our approach of finding aliases works reasonably well. There's few inconsistent ones, but the majority is consistent, and there's a big portion that is actually very strongly consistent, where TCP timestamps give us a really high confidence that this method of finding aliases works. Good, so for you to take away, if you use an IPv6 hit list, it can contain large clusters of aliased prefixes and aliased IP addresses. So in our case, half of the IPs were basically the same machines. If you use multi-level prefix detection, you can also, with higher confidence, cut out the small pieces that are actually not aliased in a space of an alias prefix. You can use fingerprinting or some other technique to really boost your confidence that what you did to find these alias prefixes actually worked. And yeah, the paper and plots are online. I've put the link here, and there's also a bunch of other stuff that I'm working on and happy to discuss offline with you. Thank you.
Eric Nygren, when you're looking at this things behind a prefix, are you have this topic of like same host? How do you handle load balanced clusters or think about load balanced clusters in that sense? Because I'm aware of some cases of this where you'll have a IPv6 prefix where most things will answer, but instead of being a single host that it's going to, there's some sort of load balance on those things. So any given IP within that prefix might go to some set of machines within that cluster, but they're still logically the same and still might result in a larger hit list than you'd necessarily want to be monitoring.
Yeah, so if I quickly synthesize, you're saying if there's a load balancer, it might actually be different machines, but all the IPs might seem to respond, but not from the same machine.
Right.
Yeah.
And do you consider that to be a single host, or does that just get disqualified?
So the initial method would classify that as alias because all these random IPs respond. With that validation step we do, we would not consider it alias because the different machines would probably have different characteristics in these small fingerprinting details.
Lorenzo Coliti, we keep hearing about this sort of attack, and with more end-to-end connectivity coming back, we'll see even more of it. I was wondering the other day if we could say, look, any field in any packet that's reserved should be random. And I think that's sort of not forward compatible because you can agree stuff, but then you basically when implementations get updated to actually support the options that that were previously random, they might actually interpret it. And I'm wondering if there's any solid way to do that, like sort of require that every option has its own checksum or something like that. So we can basically fill everything that's currently unassigned in a packet with random data all the time, and require that protocols do this, and then make sure somehow that when those option numbers actually get allocated, we can validate them on the receiver. And that would be sort of like a more structural approach to this kind of, yeah, we design something and then, people figure out how to sort of, understand like what is actually behind it. Because a lot of our protocols just say reserved must be 0. And we faithfully do that. And, here, right, you could say, well, I'm just going to send a random TTL on replies and randomize other stuff. So just a thought, really.
Just to understand this, are you proposing to always use all defined TCP options and just put random crap in there?
I mean, a lot of protocols already do this, right? Like we're just going to set random options all the time, right?
It's just like, it's a lot more data, right? You send over, it's a lot more overhead.
Yeah, but the overhead is generally sort of a small minority compared to the payload. So if you're, I guess it boils down to how much you're willing to pay for privacy. Because in this case, right, if you don't have, it's a lot more difficult. Right?
So yes, basically there is some steps that you can do to increase your privacy, to protect yourself from the fingerprinting. You could, for example, just rotate the TCP options that you send back. Also, since version 4.10, Linux uses randomized start values for TCP timestamps, so that doesn't work starting from Linux 4.10. So I think there's reasonable steps you can take to avoid that fingerprinting.
No, but what I'm talking about, like instead of like doing that tactically once the attack's already in the field, how can we sort of more design protocols to be robust to this type of thing as we design them and as the implementations basically get written?
Tobias Wiewig, TU Delft. First comment on the previous question. I think the problem would also be if you fill up random, you basically end up leading your entropy to the internet because you have to have a lot of random to put in all these packets you're sending out.
I would like to take this discussion to a different working group or the hallway.
And the other thing is, did you compare, so we have this data set of IPv6 reverse DNS zones, and did you compare the zones we tag as dynamically generated with the ones you identify as like clusters from other hit lists?
I did not do that part. If you sent it to us in your dataset, we did.
IPv6.farm. Online available. IPv6.farm or datasets are online and available under that address. So also for the rest of the room.
Yeah, we've been in contact before. Yeah.
Igor Lubashev. To continue on a little bit more to explore Eric's question about load balance clusters. You can have a load balance cluster with pretty large prefix behind that it's serving, right? And it may have not many machines, like under a dozen. But if effectively all the IPs that say they are randomized as they're going to the backend servers, so your second method will classify it as several million different machines or still under a dozen?
So if you, just let me repeat it again. If you have a large prefix and several load balanced chunks in it.
Well, and let's say the backends pick up, get load balanced randomly from that large prefix.
Probably that would be considered not aliased, because as soon as you end up on a different server, some of these tests will start to fail. So
right.
I'm quite confident that we really only count it as aliased if it's the same machine.
Yeah, if you could try to classify it possibly into not just one bin or multiple, but like keep track of maybe several alternatives based on timestamps or something else that could help.
Yeah.
I'm Jim Metatir. I'm just curious whether you identify what kind of host that has like a very huge address space such as /32. I can imagine the /64 is occupied by a single host, but /32 cases like /32 seems to be very strange. So I don't know if you have any idea about what it is.
So we found 1/29 that was basically all the IP addresses would show you the same Nginx is working on this machine website. So we even found /29s that were just the same machine.
Okay. Very quick, but please.
Just a random thought, maybe that's a firewall of some sort that does proxying.
So it looked like a web server because it had this Nginx thing.
Thank you very much. Again, have a look at the presentations on Monday. They were like more focused on TLS and HTTPS. And I hope you come back with more results next time. Thank you. Go ahead.
Hi, I'm not Anna or Ian, but I am Gori. So this is a paper that the three of us put together for TMA, and the full text of the paper is available, open source. So you can look at that. That's in the final URL. The paper was about measuring the usable maximum packet size across an internet path. And I've changed this talk to talk about how can we make PathMTU discovery work to try and make it more IETF focused. Okay, so how do things work really? It's good to send big packets because the internet can send big packets, and we have something called PathMTU discovery, full standard IPv6, works with IPv4. It's just a network layer mechanism. You have a certain size of packet you can send. It's supported some places, not other places. You get an ICMP message back. You choose a smaller number because that's what works. Hey, it's cool. It doesn't work. That's what the talk's about. Path to big messages, ICMP messages, v4 or v6, are somewhat unreliable. We know ICMP firewalls drop this, some CPEs drop this, ECMP, tunnels, other firewall processing, corporate domains, all drop ICMP and black hole the data when you try and send a big packet because you never know that the data was too big. So big packets don't work. But, and if you've been in the transport area, you probably know this, we can do things at the transport layer. The transport layer can figure out that packets don't get through. So when it discovers this, maybe it can decide to just send less. Aha, we talked about that in the IETF as well. So that's the background. Here's the first fix that came from the community. Okay, so TCP is the most common transport still, and QUIC might emerge soon. With TCP, the server side advertises an MSS, the biggest size of packet it can accept. And it sends this through the network, and the client then knows that you can't send packets bigger than this because the server doesn't want them. So how about you just change that number in the TCP SYN packet, change the MSS option to a smaller value. So in this case, the CPE changes the value from 8960 down to 1452 to be helpful. It's called MSS clamping. It's quite widely deployed, as we'll see later. So, given we know this stuff happens, we did some measurements. The first set of measurements are taken from a set of data centers going to the top 1 million web servers. And yeah, we tested them. We have 4 million points in this data set. And let's look for IPv4, what we saw. This is the MSS seen in the SYN coming from a web server somewhere in the internet, looking at the top 1 million. And for IPv4, we see 1460 as the common number, which is what we might imagine. And this little tail off across the bottom, about 25% or so of locations returns something smaller. Maybe there's tunnels in the way. Maybe there are some link technologies which are different. So there's a kind of distribution that looks like this. For V6, the shape of the curve looks like this. Oh, that's odd. This number is what you expect. This number is not what you expect. So where did 1220 come from? Well, if you followed the V6 ops scripts, you would know that there was an ECMP problem. ECMP load balancers don't know how to return the path too big message to you because they have two potential places it can come from. Life gets difficult. So the first hack that was put in to fix this was simply get the servers to advertise a smaller MSS. 1220. Now everything works, yeah? And Akamai, who did the work, saw this as an interim problem, and they described how to fix it on their web page. Obviously, they fixed it for this, because v4 no longer does this. but not for V6. Oh, but really, this isn't quite this story. V6 world's not as big as we think it is. 80% of these points on this IPv6 curve were actually served by Cloudflare servers. So really, this is reporting on two different server configurations that are out there. If you work for these people, you might want to talk to us because you could probably fix this. Okay, so that's a bit odd, but let's go further. Let's look at what happens on these paths that advertise an MSS that's smaller than the maximum you might imagine. So we do the same test, and now we run a ping packet with the full size you might expect might go across. And lo and behold, 93% of them were reachable with a big packet. They just reduced their MSS. They didn't actually change their links at all. Okay, so well, that's an interesting data point. And as we use Quick, we know we can actually use these big packets, so that's good. Let's look at edge infrastructure. All that was taken from a place that was well connected. So if we now take some mobile clients in mind, we used a testbed called Monroe that had a number, hundreds of mobile nodes across Europe, and we could launch test campaigns from these sites. At latest, we used RIPE Atlas probes to look at the wired case as well. So these green measurements are from the edge. Oh, even stranger. We did our test, we got the results we expected. Then we sent some packets without an MSS option, SYNs without MSS options. Lo and behold, we saw packets arriving with an MSS option set helpfully by the network, clamping this to a smaller value. Oh, that really is odd, and perhaps even odder, I have no idea why these numbers were chosen by these particular operators. This is not a name and shame. We have bigger data sets, and I mean, each operator just has chosen some number to clamp to. But these are 1400 or 1410, 1420. 888 hops, that's 21% of our data set, added an MSS option when we didn't ask for one. Okay, maybe there's something about not looking at this MSS option in future. What about the wired edge? Okay, turns out mobile operators weren't as bad as you think. The wired case varies wildly. We had 3,000 RIPE Atlas probes, and we surveyed a number of different places. 4.8% of our probes arrived carrying an MSS option as well. And some of these were even bigger than the maximum allowed by a 1500 byte Ethernet link. And yet we know they were on Ethernet links. So, oh dear, people are adding MSS options and clamping, but they're doing it not necessarily in a very obvious way. People are trying to help. Well, always good to have help. So, let's stop looking at what the network does, because there's a lot of data in our paper, and I've got the link to the paper at the end of my talk. Let's instead now try and use PathMTU discovery. So in this case, we use a tool called Scamper. Many of you know this. We also use Nettalyzer and Traceroute. We set up a node in a place where we could control it, and we artificially reduced the MTU of the link. And we saw whether the remote server could choose the right size of packet to send to us. So for the mobile edge, a 1500 byte packet was sent as a UDP probe. We set the DF flag for IPv4. For V6, it was already set. And small data set, but basically, the mobile operators were doing well. That's good. What about for the actual data with V4 for wired networks? This is Scamper connection. So the first line is the MSS was reduced in our connection, and therefore we didn't actually do the test, so the pale one needs to be ignored. 60 or so % of paths actually used PathMTU discovery and worked. Is that good news? Maybe. Not so brilliant from a transport perspective if you think that 40% didn't succeed in doing the thing you thought it was going to do. About 20% failed because they failed to get the PathMTU discovery to work. Some stacks didn't set the DF bit when we asked them to do it, which is a bit annoying. So that accounts for the 12%. Some networks cleared the DF when we set it, which is very helpful because then the packet got fragmented. That's perhaps why V6 doesn't allow this. So that's the kind of left side of my plot. The right side is where we now filter all the ICMP messages. So we black hole the ICMP messages. Life gets a little evil here because PathMTU discovery succeeded in only 8% of the cases. Because their PathMTU discovery algorithm had a way of detecting this and dropping back somehow, commonly called black hole detection. So, not brilliant news. What about V6? Must be better, eh? 95% succeeded. That's good. Except that, remember, many of these paths didn't actually send big packets anyway, so it's not as good as it seems. Paper's got a lot of detail in, and I'm happy to talk about the detail, but really you should read the paper and look at the plots if you're interested here. What's the takeaways? PathMTU doesn't work reliably. It's a nice thing to have down in the IP stack, in IPv6 and IPv4. If you can make it work, that's cool, but it really doesn't work reliably. The obstacles are actually obvious, but the useful thing perhaps in the data is we actually tested them and figured out where it doesn't work and how likely it is that problems occur. Path to big messages often don't get there. Some path to big messages are just simply wrong. There are CPEs generating path to big messages with some bytes just set wrongly, probably just copying the wrong bytes of data here and there and then sticking it in the packet. There are path to big messages that you can't check where they come from because there aren't enough bytes. Surprisingly common v4 configuration is only return 8 bytes of packet header, even though the host requirements for v4 say return 576. They probably didn't read the host requirements document for v4, which has kind of been out there for a while. Anyway, a smaller MSS is commonly the way that people have used to control this problem. They simply lower the MSS for PathMTU discovery for TCP, which means that many servers don't really do the PathMTU discovery algorithm anyway. MSS clamping is common in the network as well. How can we make PathMTU discovery work? Because, I mean, I'm here to try and make the network work. That's why I come to the IETF. Well, first of all, we have some measurements. And I love having measurements to start with. That's why I'm talking here. And we're going to get more. We've already started getting several million more data points to try and really understand the idiosyncrasies. The issue here is we really are concerned more about the cases where things go wrong than the high percentage of cases where things go right, because you really want this discovery to be reliable. You can make it reliable. We invented something called TCP PLP MTUD, which is basically an addition to TCP that does the probing in the TCP stack. In theory, this fits it for TCP. It's RFC 4821. We've been asking people to use this in the IETF. Big sigh again. Unfortunately, the implementations of this are slightly broken. Maybe because people use MSS clamping, they don't actually exercise the code, so nobody cares enough to fix it. But many of the PLP MTUD implementations we looked at were either not enabled or they were not really functional. And didn't do harm, they didn't do anything useful. So TSVWG has a work item. It's called this. It's looking at doing PLP MTUD for datagrams. We're starting afresh. We are making something that will work with UDP. It will work with various applications running over UDP, including Quick, hopefully. We have some hackathon activity to make this work with Quick, also with SCTP. And we think this might be a good solution to this problem space. And with the measurement data, we might be able to build something that's robust and works reliably across the whole of the internet. Maybe in future, we could come back and redo the TCP thing in a similar way and try and get TCP working in the way that we finally managed to get datagrams working with UDP. I promised you a more detailed copy of this. It's available in our TMA paper. This is an open access publication. You can download the data and you can download the paper, and we are doing more work. Questions, please.
Aaron Falk, thank you for this great, very interesting, so much, I'm still digesting what you've said, but it seems to me that you're, what you've highlighted is that some of the problems are in the network and some of the problems are in the end systems. And it looks like the stuff that you're proposing is focusing more on making things work in the network. Are you also doing something to get end systems to correctly make use of the M2 discovery? And just an aside, I think that DPPLMPTUD has got to be one of the worst acronyms I run into in the idea. It's like
it's actually not. Yeah, well, we thought it was so long we were going to keep it for a while.
On that.
No, I think TCP/PP/LP/MTUD is actually worse.
Right. Okay. So the first answer to the question is what can we do with the data and how can we use it usefully? I think just understanding these things, we can immediately start talking to people who maintain stacks and say, hey, look, this stuff's going on and you might easily be able to fix this. That's cool. I think the real solution is to fix the transport protocols to work with this. So there's a bit of work going on with the stacks, and maybe, I don't know whether we can really change the operational practice of network operators. We can tell them about it, they can learn, and maybe some will immediately adjust. I don't know. Who's next?
Okay. So my question is very quick. My name is Yoshi Nishida. Have you ever tried to locate where is ICMP black hole? There is a way to, I think, if you have this data, I think you can, to some extent, locate where is ICMP black hole, I think.
Oh, we can. The tests I skipped over quickly were expanding ring searches, where we actually found the piece of equipment and where the MTU dropped and whether it dropped more than once on the path. So we have the data for it, and that will help us now construct test cases for datagram path layer MTU discovery. And I think we will make those available to other people.
Yeah. Do you have any other characteristic of the distribution of the black hole?
Yeah, the characteristic is the internet's quite broad and very varied.
Okay.
Can I just say it's packetization layer, and it's Brian's fault that we keep saying path.
It is, isn't it? Yeah, okay. Where's Brian? No, sorry. Please go.
Oh, thank you for presenting this. Having been involved in some of the V6 load balancing a while ago, this is just like, so ICMP based is basically unfixable. And thank you for clearly showing that. And I think doing it at transport layer is the only way that will ever work, because it shares fate with the traffic that you actually want to work. And so I think the key things there are, don't ever black hole, which means start small and like try to grow, and don't ever increase latency, which means parallelize, right? You have to, you basically maybe send the same packet with the different sizes if you can. Because so those are going to be, because like MSS rewriting has kind of those properties for TCP. Now you can't do that with any encrypted protocol, but I think those are the drivers, right? We looked at this when we were doing the V6, the first V6 flips at Google, and you've got these hurricane electric tunnels where the MTU of their network is 1500, but the tunnel is 1280, and they don't know that they have 1280. And so you send the packet, gets all the way there, and it hits this IP, and you lost an RTT. Was that right? We can't do that, because if we impact latency, we'll never ship this thing at all. And so 1280 it is. And so at the time, at least for a very long time at Google, I don't know what we do now, the outgoing MTU, we never sent anything that was better than 1280, no matter what you announced to us, because we knew it wouldn't work. And even if it did, we'd have this latency impact. So think about that. Good luck. Thank you. Thank you for taking this on.
Thank you. I'm not too sure I'd buy sending the same packet twice with same data twice, two different sizes. Maybe I would send a probe, which is what we're kind of talking about, that has no real content, but we can actually verify that it got through. And we don't...
As long as it shares fate, sure, yeah, absolutely.
Yeah. And we don't try and raise the actual packet size of the real data until we really know that it works. Jana.
Jana Engar. So I want to agree with what Lorenzo said. And I want to take it a step further, in the sense that I almost think that TCP, PLP, MTUD should be the first one to explore. The reason I say this is because it's a full-blown transport. It's something that we can run traffic on, and we can actually measure and see how much latency difference a particular mechanism makes or doesn't make. And that makes it viable for deployment. If you have real traffic using a mechanism and showing that it doesn't cause any latency increases, but it actually allows you to discover larger MTUs if they exist, then that's a valuable mechanism that can immediately go into other things as well. I absolutely agree with not relying on ICMP messages and going in the direction of doing PLP MTUD for TCP, and I think this is a problem we should solve. It's okay. It needs solving and it should be solved.
So why is TCP a little harder for us to work with than with the UDP and SCTP stacks? The answer is simple. We can't actually send a non-data segment through the network and verify it got to the other end, because TCP doesn't let you do that with a size. There's no padding facility in the TCP header. So that's not a problem. And Mathis's RFC, which I mentioned, has a way of dealing with this. But the way of dealing with it is he interacts with the recovery and the congestion control mechanisms directly. Whereas if you can send path probe messages, which are identifiable to you as probe messages and can be echoed, but to the path they just appear as packetization layer messages, then you can separate these two and develop the algorithm quickly and efficiently without worrying about that other interaction, which can then be addressed by the transport.
So that is actually part of my motivation for asking it to be in TCP, that interaction needs to be understood.
Oh, yes.
And not just does need to be understood, I think it's an interaction that's important to resolve, because without that, again, you'll get zero deployment. We don't want to go through the process of trying to figure this out again and basically not have any deployment. So in that vein, if doing it in Quick is easier, then that's fine. Quick has the ability, you can send padded packets and you can do all of that. But the interaction with loss recovery and everything has to be resolved. I will say one last thing.
Well, on that one, come join us. We're playing with Quick code.
I'm sorry?
Come join us from the congestion control side. We are playing with Quick code. So we're interested in seeing how that works in Quick.
Yes.
And we do intend to go back to TCPM if we have cycles in the end to revise Matt's draft if Matt's open to looking at that.
That sounds good. You called Quick an application, and I would take that back and call it a transport, because I think it's important to make sure that we aren't building generic mechanisms for UDP, but we are building specific mechanisms for transports like Quick. Thank you.
Okay, thank you.
Eric Nygren, based upon what you've been looking at, do you see any value in the path-based signals, such as the MSS clamping? Like, is the MSS clamping something that is useful and helps here, or is it something that as we start having encrypted protocols such as Quick are worth looking at and exploring ways of getting signals from the path, similar to MSS clamping, or is it a dead end that we should run far away from?
I'm going to hide my blue dot. As somebody just talking. It'd be nice to have better signals from the path. MSS clamping wasn't the right thing. You were taking a side effect of something else, and you can stick any number in that you like, which is what we saw. Some people raising it, some people lowering it, some people creating it. That is a hack. Thank goodness we can't do that with Quick. Could we do something else? Yeah, possibly. Ron Bonica's talking about some truncation method that might work with V6, with sending probe packets through the network that you can somehow interact with the routers to figure out what really works. It could have some value, I don't know. I think my immediate takeaway is you've got to do this at the transport layer. It's got to be part of Quick, it's got to be part of TCP, SCTP, something that understands how the UDP stack's operating. It can't just be done in the network layer part.
Yeah, trying to figure out if he still wants to say something. Okay. But
I guess the next speaker could come up anyway.
Yeah, it's fine. We can move on. Thank you.
Yeah, good morning, everybody, again. So this work is done by me, John, and ISI, Mertz at IDN Labs as well, and Twente, Ricardo in Passo Fundo, Marco, which is also sitting here in the back. And it's currently under review. And we call it when the dike breaks, the second DNS defenses during denial of service attacks. We have seen that there's a kind of growth in the number of the denial of service attacks lately. They're getting bigger, more frequent, and cheaper as well, and easy to be performed. So I think the latest numbers that we have is they have reached 1.7 terabits per second in 2018. Last year, Dyn, or 2016, no, last year, Dyn had a 1.2 terabit attack on the DNS infrastructure. It was done to use Mirai botnet, was the first big botnet doing attacks that we know. And you can actually buy DDoS attacks now as a service on the internet. The services are called booters, they call stressors, but you can buy them. And we have seen also the DNS as being target of DDoSes. And in particular, there have been 2 cases of denial of service attacks on DNS. And the problem with attacks against DNS is that breaks down everything else. If you cannot resolve domain names, your internet's not gonna work. But there are different types of attacks. So if you look at the left, there was an attack that happened on the root DNS service in November 2015. And this page here is the DNS mon from RIPE. And everything red here shows when they had reachability problems. And even though some of those root letters had problems, there were no known reports of errors seen by users. And that's kind of strange. So it's good for DNS, even though they had problems, nobody kind of noticed from the user point of view. But on the other hand, the attack on Dyn, a big DNS provider in 2016, made it to the news everywhere. This was in New York Times, The Guardian. Bruce Schneier was writing about that too, and a bunch of other places, because some users could not reach their proper websites. They were like, I think, Netflix and a bunch of others, New York Times. So if the user cannot connect to the main applications, you're gonna have a problem. And the question that we wanted to investigate was like, well, these were 2 large denials versus attacks. They have very different outcomes from the point of view of the users. And the question is why? So we wanted to know what factors actually impact this experience, what causes no change in the or sporadic problems. We know that the recursive servers on DNS, they have like various mechanisms to cope with that. Caching is one of those, retries as well. And we want to know if operators can improve their services as well. Now, just a quick recap on DNS. This is a figure showing how pretty much DNS works. So if you're a user, you're here in the stub resolver and you wanted to know an IP address, let's say, from a particular domain. And the green guys here, these are the guys who know that they have the information. They are called authoritative servers. So somehow you have to get there to get an answer. But usually you don't go directly. You have a bunch of recursive resolvers in the middle. These are the guys who are going to do the job for you. And there's, if you're familiar with DNS, you know pretty much how that works. But what matters is these guys here, they may have caches in between. So if somebody else asks the same query again here, they're going to cache and give a query much faster. And if there's a problem here, they can, with the green guys here, these guys in the middle can retry to switch for servers, to retry and do a bunch of things. And DNS records, they stay alive at the maximum, usually for as long as, for a value that's specified as a TTL, time to live, for the record. So this guy here, the green guy, will say, hey, you can store this record up to 1 hour, 30 seconds or whatever. So it's stored here, and then this will later go to the caches. Now, how can we evaluate the built-in resilience of DNS? So in this paper, what we've done, we broke down this into 3 parts. The first one, we evaluate like how caching really works in the normal circumstances in a controlled environment by using like in the wild, we're using RIPE Atlas. And then later we moved to a production zone. We analyzed .NL in the roots, but in the presentation and only covered .NL. That's the one I work for. And it's the graphs that I have here. And later, the part which is more interesting, it's we emulate denial service attacks in the wild to observe. And the goal is not only analyze how the authoritatives behave, we wanted to know how users see that because, well, that's the goal of our paper. All right, so how did you do this measurement for part 1? So you wanted to know how caching works. We'll register a new domain that has never been registered, cache test.nl. We run 2 authoritative image servers in EC2 in Frankfurt. We don't analyze any cache here. That would add a lot of complexity, but we have a bunch of work of any cache if you're interested. As vantage points, we use RIPE Atlas. There we use 10,000 of those, and we consider vantage points in this measurement, not only the probe itself, but a combination of probe with local recursive. And each probe they send a unique query, which is identified by their probe ID. So we don't want to, when someone asks a question, one probe asks a question, you don't want another one to ask the same question, so you can interfere in the caches of each other. And we encode in each answer, we have a quad A answer information in a counter there that allows us to identify later, is in the paper, I cannot cover here, but allow us to identify if a query was answered by the cache or by the authoritative. We kind of increment this over time, so we can actually determine that very easily. And have a bunch of scenarios. We play with these TTLs and to measure the influence of that. All right. So what do we control? We control the stub resolver, that would be the vantage points and rep atlas, and we control the green guys here. We have no control here, and that's what we try to measure in this paper. We wanted to measure how resilient your recursive layer is. Okay, let's get to the results. How good caching is in the wild? What you see in this graph here in the x-axis are different experiments. By the way, all the data sets are open. You can check on the website, on the paper. In each of them, you have the TTL we use in authoritative name servers. And these are the number of queries that we observed. And each query we classify according to 4 categories. The blue ones in here are the ones that correctly went to the authoritative. They were answered, and they should have been answered by the authoritative, so they're fine. The green ones here, it's the cache hit. They should have been answered by the cache, and they were. And what we would see, so this is also good. And what we see here is that caching working, it works. It's fine for 70% of the times when it should work for the 50,000 VPs. And this is considering our not very popular domain. So people were asking for the cache test.nl, called A record, and this is not very popular. So only we were actually querying that. So I would expect to be even better. So this is kind of lower bound for that. But it's not so good news is that 30% of cache misses. This is shown by the yellow color here, the AC, and we are like, okay, so they're on the wild here, we see 30%. And why is that? There's a bunch of things. Caches may have limits. Our domain was not that popular. Caches may be flushed and the recursive. And I refer to caches, remember in the layer that we have no control, the recursive. They're very complex caches. A lot of people now use Anycast in the recursive layer. There's a bunch of free services out there, and some of them may have cache fragmentation. So we went further. We went to analyze what happened with the queries that are not answered by the servers. They were actually cache misses. And turns out that half of them are using public service. And this is, you can see the classification did. And half of the ones that are using public are using Google. Again, this is a not popular domain. I would expect to Google behave better in a popular domain. So, all right. So this was in a controlled environment. We use in the wild, using Rep Atlas. But another question you may have, all right, how that would work in the production zone? So I work for that now, and we have access to the data that comes to our authoritatives. So we just compute the time in between 2 queries that gets to us from the recursives. And for each recursive, we compute this time, and we choose a domain that was our authoritative name service that we announce on the zone, and you know the TTL that one is 1 hour. So this is the number of queries that we analyze is 6-hour period. For this number of recursives. And we see that roughly 70% as well of the recursives, this is a CDF here, they actually query around the time of our TTL. So what it means here is that our experiments are also like the real zone. You can confirm the same here in a production zone that I know. We also look into the roots using detailed data. It's also in the paper. All right. So what do we have so far? We know how caching works in the wild. And with that, as a sort of a baseline, we can move to the interesting part. And interests me, it's like, how can we know that caching works also during stress, during a denial of service attack, to understand the user's experience? Okay, so how are we going to emulate a DDoS? Well, we could have just tried to DDoS our services to Amazon. I don't recommend that. That would create a lot of problems. So what we do, we emulate a DDoS on the same service at Amazon. I just use IP tables, and I say drop 100% of the traffic or 50% of the traffic. That's a kind of approximation because servers under stress are going to drop traffic. It's not exactly like a DDoS because in a DDoS attack, you can have like links congested, routers having problems as well to forward the packets, the queues, and a bunch of other stuff. But it's a good approximation for that. And again, we control only the authoritatives and the control here is guys, but we don't control anything here. And you want to see how, if your recursives after you actually got your back once there's a DDoS here, and if you get an answer. Now, first scenario, this is a complete DDoS, means the server will drop 100% of the packets, and the TTL is set for this one is 1 hour, 60 minutes. This is doomsday scenario for an operator. If all your authoritatives are down for, in this case, for 1 hour, this is the worst that can happen, and you wanted to know how much caching can actually protect. So in this figure here, you see like an arrow going down, and this means the time when you can start to simulate the DDoS. So you allow all the probes to send one query before we start simulating, so the queries, the caches of the recursives get populated. And after that, we actually start dropping all the packets. And next time there are more queries, we see like the blue guys here show people that are actually getting an answer, and you see a continuous drop until here is the time that caches expires and very few people get an answer. Like all the other cards are not getting an answer, they're having problems, so people cannot resolve the domain. But what we see here is that 35 to 70% of the clients here are answered by the cache, I'm sorry, even though the authoritatives are down. So this is very good results. It's also very interesting here that even when the caches should have been expired, 0.2% of the clients are getting answers. And there's a draft in which unfortunately expired. It's called serve stale, which means like, you know, if a recursive cannot reach an authoritative, serve the answer you knew beforehand, and just to serve an answer. So that's exactly what's happening here. There's a very little, very small number of people getting that, but I think it's a good idea. All right. So now let's change another parameter, another scenario. We're gonna carry on with more doomsday scenario. That's 100% failure, packet drop, and then recursives. What you're gonna do here is like, instead of only allow one query before the DDoS, you're gonna allow like 1 hour, which is pretty much like the TTL. So the caches should be more or less about to expire when you start the DDoS. And what you see here, the number of people getting answers during after we started DDoS is far lower, meaning that cache is much less effective as timeouts near the attackers, or cache timeouts. And some of people here, the blue guys, are getting an answer because of, incidentally, because of fragmented caches, which is also very interesting because they end up filling up later. And this second error here, I just decided to switch up the server again and see how quickly they would catch up. And you'll see that very quickly all of them catch up, all the recursives. They bounce back once the servers are up. So the bottom line for this graph here is that, you know, your clients are not going to get protected for how long your TTL is available. It actually depends on the state of the cache at the particular moment that happens. If your record's about to expire, you know, you're on your own. All right. So we also want to know from the previous graph, you're going to now reduce the TTL from 1 hour to 30 minutes. That means that the record should be in the cache now, not only for 1 hour, but for only 30 minutes. And you can see, if you like, if the recursives have a problem, the recursive will have 100% packet drop. What we see here, again, the drop is much quicker now because the TTL is smaller, so the records stay for shorter periods of time in the cache, and some people here get a stale answer after the cache expired. So for the operators here, for DNS operators, and for anyone who uses DNS, think carefully how you choose your TTL of your records, because you may wind up shooting yourself in the foot if it's too short TTL, because you're gonna, you'll be undermining the protection that the caches can deliver to your clients. So this covers complete DDoS attacks, which means like the servers could not give any answer. Yeah, I just talked about that. But there's cases as well, what we call partial DDoS. It's DDoS attacks, they attack the authoritative name servers, but they're not strong enough to bring all of them down at the same time. That's exactly what happened to Dyn with the roots in November 2015. And some other servers go down, some of others they don't. So you also wanted to know, in this case, how users would experience the attack. So now it's not doom days anymore, but it's a very realistic one. So what do we do here in this particular scenario? We have a TTL of 30 minutes for the records, and we drop 50% of all the incoming queries on authoritative name servers to simulate a DDoS, simulate a 50% packet loss. And it's very interesting when we start a DDoS, when the arrow goes down here, we see like most of the users don't even notice anything. Most of the users get an answer And I think that's a very good result. This is shows the resilience of DNS. And the only thing they would notice, this is the RTT on the figure here below. You see the latency actually, and you see that there's an increase in the latency, so they take longer to resolve their domain name. But they're getting answers. And let's play a little bit more. Let's make the case worse now. Let's keep the TTL, but let's drop 90% of the traffic. Let's see what actually happens. Even with 90% of the packet with this TTL 30 minutes, most clients in the blue here, you can see between the arrows, they get an answer. So this is, for me, is an example of good engineering. People who have developed that, who have built this into DNS, I mean, they deserve the kudos for here, because 90% packet loss and like 60% of people get an answer. This is fantastic. And don't get me wrong, once somebody gets an answer, that goes to the cache of their recursive, so next time they come back again, they can fetch the record. So this is like coming together, all these things, all the good practices. Let's now move to another case in which you set a TTL to 1 minute. And if you set the records TTL for 1 minute, that means that nobody should get an answer from the cache. Very few people, only if they serve stale. Because once they fetch and they come back 10 minutes later, it's already expired, the record. So you want to see when you have 90% packet loss, all your records have a TTL of 1 minute. You see that like even with no caching, theoretically, I mean, you can serve stale, 27% of the people get an answer, even though you have 90% packet loss, which is, for me, again, a very great result for DNS. Again, you see there's a different impact here in the latency. It goes much higher because, well, they have to do a lot of retries. You're going to analyze next. But it's still very good results, especially for operator. Yeah, all right. And on the previous graph there, the success of DNS was doing to retries, or what the authoritative names with the recursives would do. If they're not getting an answer, they're going to switch from server to server, and they start to retry and a bunch of other things. And in this graph here, we show a time series. This is measured at the authoritative side, the side at Amazon that we control, and we show the number of queries during number of operations. And for the 90% packet drop with no caching, we see an increase of 80 times the normal traffic. And this is like not a DDoS, this is like friendly fire. This is like your recursives going crazy, and they cannot actually, not actually going crazy, they're doing their job, they're trying to resolve a name. They cannot get an answer, they try it again, they switch to another one, they try again, until they get an answer. So for an operator, if you're under DDoS, what this means that like, you're gonna get a lot of friendly fire. I mean, your client's gonna try to resolve that, so be aware of that. And if you actually over-provision your DNS server for 10 times your normal traffic, be aware if you have 90% packet loss, you're gonna get this number of people hammering you. So your traffic, 8 out of or 9 times of your traffic is going to be just your friendly fire. So be aware. So implications, caching works and retries work really well. So kudos for the DNS community who had built this. Provided, especially if some authoritative stay partially up, that's really great. And caches last longer, and provided as well that cache lasts longer than the DDoS. For the DNS operators, one implication may have, like, if you can keep one up, things are kind of going to be fine. So you can make one of your services very strong, but it can be very careful. You can be very careful with loads of distribution. We wrote a paper last year in IMC showing when you have multiple authoritative name servers, what happens if one is better than the other. So you may have a want to look at that. The cool thing about this paper is like it can explain why the root DDoS outcomes of the particular attack happen, because the roots have a very long TTL, 1 or 2 days if I'm not mistaken, 1 or 2, I think it's 1. So they're going to be in a cache 2 days, 2 days. And a lot of people cap the TTL for 2 days for 1 day, but it doesn't matter. It's still a long period. The attack was shorter than that. But we can explain that now. And there's a clear trade-off here between TTL of a DNS record that authoritative serves, sets, and the DNS resilience. So be careful with that. And many commercial websites, especially, have short TTLs, because a short TTL, when you change something in DNS, is very easy to propagate. It's very quick, much quicker. And you can explain that, the pain of dying customers and users' perception. And just to give an example, I had a discussion with some folks from Amazon, and if you use their recursives, they're going to cap all the answers to 60 seconds. So just be aware of that. Conclusions, let's move to the conclusions then. So this is the first study to evaluate DNS resilience to DDoS from the user's perspective, trying to figure out how the recursive layer works and how caches retry work under stress. we evaluate design choices of various vendors using measurements. We actually have no information about, very little information about the recursive resolvers layer, which software that are using. We actually didn't care. We wanted to see in the wild. That was the goal. So caching and retries is very important part of DNS resilience. So if you're under attack, people do filtering, people do scrubbing, do a bunch of other things, but DNS has already built in a lot of good stuff in it. Our experiments also show when cache and retry works and when they don't. It's consistent with the recent outcomes, and the DNS community should be aware of this trade-off. And I think it should. That's my personal opinion, but I'm not sure what the community thinks. That it should advocate for serve stale deployment, because it's your last resort when things go really, really bad. So I have a tech report here. This is my mail. I would like to thank RIPE NCC for all the measurements again. They support us all the time. And all those people, Wes, Dwayne, Warren, Stefan, and Martin, for reviewing the paper. And the title of this paper is When the Dike Breaks. So this is a dike close to where I live in Holland. You can see the water level is higher than here. So if it breaks, I'm going to be swimming, and I hope that this never happens.
John Reed, one thing that I thought was interesting is when you simulated partial authority failure, I think you did packet loss either 50 or 90% on both authorities. Is that correct?
Yeah.
So one thing that I think might be interesting for future work is a complete failure of a single authority and the other's 100% up. And then I think because, in theory, the recursives should, as they go through the source list, penalize the non-responding authority. And I think it might be interesting to see how that actually performs in real life.
So I think I might have that in the paper. I ran that actually as well.
Oh, okay.
Yeah, and I can give you an answer right now. It'll be just. I can tell you it's going to be just fine. I remember the results, because if here you have what they're going to do. We have an IMC paper from last year that shows if one doesn't answer, they move to another one and they get an answer. So all of them are going to get an answer. I'm not sure. I would have to double down, check the paper, but I think I remember the results. They all get an ansser.
Okay, so it's in the paper that's linked.
Yeah, it's in the paper.
Great.
It's not in the paper. Contact me. I'm not sure if you remove because of space, but it works.
Okay. And then another question I had is there any opportunity, I think, for research between the stub and the recursive if one of the recursives goes down, because I think there's a lot of variability in what operating systems do when multiple recursives are configured, how they recover, et cetera. Is that something that you've ever done any research in?
So I didn't look into that. The way that RIPE works, it's like each probe is configured with.
Yeah, I know.
Yeah,
it would be difficult to do with RIPE Atlas probably, but
yeah.
I mean,
that's an interesting case. We haven't looked into that. We look at the recursive layer as a black box, and we just analyze the result. But for sure, that would be an interesting result.
Thanks.
Thanks.
Robert Kishtaki, RIPE NCC. Somewhere early 2017, we added 2 measurements to each probe. So it's a built-in. If you plug in a probe, it runs already. Measuring root servers in particular, like every 10 minutes or so, with the intention that we are trying to capture data in case there is also another attack against the root servers. So I'm not looking forward to it, but if it happens again, we will have some baseline data that is close enough to what the users probably observed.
But sorry, just to understand, you use the probes to contact the roots, or you just let them use the resolvers?
So local resolver.
All right.
Basically, we're doing 2 queries. One is for a random domain, so you expect a no answer. And another is well-known domains like Google, Facebook, and so on.
Oh, that's great.
So if shit hits the fan again, we hopefully will have some good data.
And is it built-in, like all the probes do that?
Yep.
Can you send the measurement ID in the list, maybe, to me?
Yes, I can do that.
Thank you very much.
Paul Hoffman. So I love measurement, love the stuff you do. Didn't like your conclusion that we should start looking at serve stale again. I don't think your conclusion actually matches your data because of what you just said to the last person. If one of the authoritatives is up, you're going to be okay. So an assumption that many people might make is a way for a zone to do it right is not to really worry about the TTLs so much, as well as to have enough authoritative servers. And so, I mean, you definitely measured one knob well, but serve stale deals with 2 knobs, and I don't think you can match them in this. Again, your data and stuff is wonderful. I just don't like that conclusion about serve stale.
Thanks. Yeah, I mean, like in the paper, we don't really advocate strongly for serve stale, but this is my personal. I mean, because I see like it would work in our experiments, but I agree we have to look at that carefully. But it was the only hope for people not getting an answer. But yeah. Thanks.
Okay, thanks.
I'm Jimmy Tatia. Probably related to the previous question by Paul. Have you examining the TTL or other parameters, the answers in the case of the cache expiration to confirm it's more likely to be an effect of
I'm sorry,
cache step?
No.
Did you see details of the answers in the case of?
Did I see what? Sorry.
Am I clear?
No, I'm not getting it. Sorry.
Did you see the details of the answers in the case of cache expiration to confirm whether it's more likely to be the effect of use stale,
So
like very short TTL or something?
So every answer that we get, we have a counter that allows us to tell if it was answer from the authoritative or from the caches. And I have built a cache model in the paper that once we get an answer for the first time, we start a counter. We start actually putting a virtual cache in our analysis, and then we can actually compute later if it was answered and it should have been answered by the cache. So we have all the information. Check the cache session paper.
I think I can clarify what he's asking. You had the up, down, up question. You were saying, oh, people who live through it. I think your question was, if you actually have the answer on the second up be different, you can tell which things were stretched from the first.
Oh, we have, we have, this is exactly this. Let me see. I did that for the part one. This here. So these are, we classify the answers according like, this was answered by the caches, meaning we know the TTL of each answer. So we have all this code.
Okay, so again, I think the question, the research question was, if you change what's going to come back, you can tell what had been stretched through what was going down versus, oh, now it's up again and it's getting the new answer. Is that
Yes.
Okay.
I didn't look at the transition from down to up. I just, well, but
and that might actually go to your question of should we encourage serve stale or not?
Yeah. Thanks for clarifying.
I have one more question. Can I continue? And also other related question is that I guess depending on the type of the recursive server, the deployment level of use stale is quite different. I guess commercial recursive sub operators tend to enable this kind of feature more likely. So I wonder what kind of resolvers actually tested in.
So that's a good question. We there's many vendors of DNS resolvers and there are different versions, and so what we have in the end, the population of resolvers is very heterogeneous. And what the methodology applying this paper, like we're not going to try to profile them and identify them. That's too complicated. We're going to look at them in a black box, analyze as a whole. I'm not sure if there are any other studies to look into that specifically in the lab. You can do that in the lab, but our goal is to understand that in the wild so you can actually generalize the results. So there's a trade-off, but you can do in the lab. You can do that. Say you can I can run bind there in a certain version, see what happens. You can actually do that, but we didn't do that because our question was like from the point of view of an operator and you want to know in the wild. So it's a different thing. But yeah, absolutely.
Okay,
thanks.
Hi, Giovanni.
Hi,
so
Martin.
this is Maarten Aartsen with NCSCNL. So I'm wondering what you research right now is DDoS conditions at the authoritative. So in the Netherlands, we had this incident a couple of years ago where an access network got its recursive DDoSed. And I'm wondering what part of the conclusions you think would mirror that scenario where you have an access network or an enterprise network that where the recursives have trouble reaching your authoritatives, and whether it makes any difference with respect to Paul's comments about serve stale. And I'm not knowledgeable about that draft at all, so this might be a dumb question, but I'm just wondering what happens if the DDoS concentrates on the recursives instead of, or their link to the internet.
So yeah, so if the DDoS happens on the recursives, I think depends a lot on which recursive we're talking about, because you're going to have a population of clients behind it being affected. Again, depends a lot on the kind of the attack. But I mean, I'm not sure if I can with my data, I cannot say anything about that, but what I can say is that the damage is going to be only around the people that connect to the particular resolvers. So I would expect less damage than reaching an authoritative. But usually, I mean, you can do that. Like most of the attacks we've seen is on an authoritative side. I mean, they get reported because this is more where the information is located. So I wouldn't know how to say, but I just know the impact will be smaller on the clients, unless it's a big provider like this big services ones.
Yeah. Thanks.
Thanks.
Thank you.
All right, I'm Wes Hardiker from the University of Southern California Information Sciences Institute. This is, I think, your 4th DNS talk for the day. So I'm going to be talking about measuring the DNSSEC and specifically the KSK role that's about to happen and some of the issues with it. So first off, background, I'll give you a little bit of background about the DNSSEC and how it works, just in case you don't know. Hopefully you do. And then some problems that are sort of coming up with the KSK rollover that's going to happen in October and how small they are. The case study analysis I tried to look into, well, what if we tried to really look into what are resolvers actually doing with the trust anchors they have configured, how much can we measure that? And then I'll look at the impacts of, I actually made some changes out in the real world that caused some benefits and how big those benefits are and how deceptive those benefits are. And then finally, I'll talk about some lessons learned with respect to sort of how the IETF really ought to think about deploying, or excuse me, designing protocols in the future, especially those with trust anchors. So for those that aren't familiar, DNSSEC basically has this top-down chained authentication system that basically allows you to prove that an address that you're requesting, for example, either exists or it doesn't, and that it wasn't modified since the time that the original author published it. It's signed all the way down. In order to do this, though, you have to have a trust anchor for some key up the chain. Typically, that is with the DNS roots that is run by IANA's data set and their top-level key, which is the one that's about to roll. So one of the things that we realized a couple of years ago, or I should say not, that the IETF realized a couple of years ago, was that we needed to know what resolvers we're actually using as a trust anchor. It's very hard to know if there's millions of DNS resolvers out there, how many of them are A, validating, and B, how many of them are using the current trust anchor, and how many of them have a new trust anchor deployed, so it's okay to switch. It's very hard to determine a point of which it's okay to do a safe roll because most of the resolvers out there are using your new key and it's now safe to use. So RFC 8145 was written and it's called Signaling Trust Anchor Knowledge in the DNS Security Extensions, and it basically adds one extra query to resolvers. So any more recently deployed resolvers running newer code should hopefully, when they are asking for a DNS key for the root saying, hey, what's your current key? They should also simultaneously send another query saying, oh, by the way, these are the keys I currently trust. And that way we can actually measure and watch how those keys are slowly being adopted and trusted. So with respect to the current key role, the first key that was used to sign the root was created in 2010 with the expectation that sometime after 5 years, we'd start rolling the key. So the second key was created in 2017. It was generated in October of 2017. And it was put into production, it was put into publication. So it was actually first appeared in the root zone in July of 2017, last year, with the expectation that it would be put into operational use on October of last year. And then just before that happened, so on the order of 2 weeks before, on September 27th, ICANN wisely decided to stop the rollover. And this came from this whole measurement system that I just talked about, because there was sort of some unknowns. And so the next plan is that it will roll this October instead, now that more people have had time to analyze the data, such as the data you're about to see. So this is the graph of the measurements of that 8145 separate set of signaling that I talked about. And if you actually look very carefully at the dates on the bottom, that gigantic uptick in black, which I'll get to in a minute, and black in this graph is actually the bad line, October actually existed before that giant uptick as well, so it's actually got worse since last September. But basically, if you look at this graph, the black line and the black percentages are on the right-hand side are the number of resolvers that trust only the old key. So they don't trust the new key. So on the right-hand side, which was March of this year, 20% of the resolvers out in the world that were sending RFC 8145 signals did not trust the new key yet. That had been published at this point for 9 months. So yet they had still not picked it up. And so I kind of ran into this question of why? What's actually going on here? What is it that we can learn? What is it that we can measure? So I did a few things. I wanted to know why so many new addresses were appearing too, because it wasn't just that there's these resolvers that never picked them up, but we were constantly seeing new addresses that could be coming from new software deployment, could be coming from a number of things. But why were they only trusting the old key? So I looked at two sources of data. I looked at all of the 8145 signaling data that ICANN had, which totaled about 1.1 gigs in size. And thanks very much to them for contributing that data for me to study. And was carried from January to March of this year. I also looked at all the incoming requests to USC ISI's root server, which totaled 2.8 terabytes of data. And that was only just for March. So that was a lot of data. So the first thing I had to do is sort of reduce the problem space to something I could actually look at, say, over a weekend. So I did a couple of things. One, if you look at in the ICANN data, there was 1.2 million resolver addresses sending queries to all of the roots. Within that, 500,000 of them were sending signals for the old key. But what I found interesting is that within that, 310,000 of that 500,000 were signaling only once. In other words, they only sent one signal in 3 months. That's just plain wacky, right? These are things that should be sending a signal, we'd think, once a day or so, if they were really resolvers on the internet, that were staying up. Clearly, one signal is just strange. So then I looked into the B-root data, which is line D, and of the sources that were sending to B-root in March, there was 309,000. 113,000 of those were sending only the old key, and then 16,000 were sending the old key just once, again, looking for that same commonality. And then I noticed that a lot of them, and we'll see a graph here in a minute that shows this, were only sending a couple of signals, only a couple of total DNS requests, and they sort of went away. So it'd be like these resolvers kind of coming up and then going away immediately. So to summarize this, more clearly, there was 6,702 unique addresses that sent a single, I'm using the old key query, in the first quarter of 2018, and that signal went to B-root during March and only sent 2 to 9 other requests. That's just a very strange set of data. So I kind of looked, well, what would cause this strange set of data? So quick graph, this is a CDF graph showing the number of queries sent, the number of addresses sending a number of queries. So on the x-axis, which is kind of a strange way to think about it, on the x-axis is a log scale of the number of queries sent, and on the y-axis is actually the number of addresses sending that query in March. So you'll notice that there's 63% of the sources sent 2 or less DNS queries total in a month, in an entire month. That makes no sense, right? If you like bar graphs are better, this is the same sort of graph showing there's a huge number of hosts sending a very small number of signals. Very long tail, obviously. So I kind of wondered, is there a commonality? So looking at all of these requests, I looked at all the rest of the queue names that were sent to USC ISI, and then tried to see if there was a commonality. So I looked at, again, all the ones that only sent 2 to 9 queries total. And what I found was that, of course, the highest number of queries sent were the signal for the old key, which is that strange cryptic hexadecimal _TA-4A5C. That's the query that's sent when you only trust the old key. The second most popular was the root zone. And then the third and the fourth most popular were a single domain, and to the point of 3,000 queries followed by 400 queries for a VPN provider. And so clearly I thought I had found a solution. At this point it was approaching midnight. I very quickly realized hopefully something was good, and sent a note off to ICANN staff, who actually managed to get me contact information. Woke up at 5:30 the next morning to go immediately write them and say, hey, what's up? So I also examined the VPN provider software, downloaded the Android version of it because they have multiple versions of their software, and I searched all of the files in the Android APK for the DS record SHA-256 key, looking for it. And sure enough, it turned up a root.key file that only contained the old key and didn't contain the new key. Yay, success. It also contained the libunbound DNSSEC validation resolver. Resolver library. So I reached out to them, again, thanks to ICANN's Octo staff for finding the contact information. And this vendor said, wow, you're right. It affects 10 of our software packages, and they promised to release something coming in the next couple of months. So a couple of notes here. One, I'm actually, this vendor did the right thing. They were using DNSSEC to verify that they weren't behind a paywall, verify that they were actually going to send their VPN connections to the right place. So they did the right thing, but then they failed to update the key in the long run. That being said, I'm still not going to release their name publicly, although it wouldn't be horrible to figure out. I urge you, please don't try, just for their sake. But let's look at the impact. So this is the same graph taken on Sunday while turning in these slides, and you can see the first indication where their VPN software started to be released, and there was a major drop. Only last week did the Android version get released, and actually iOS is now released. The slide's already out of date, and it's dropped a little bit since then, but it's still looking like it's flatlining. So we're back down to 8% of resolvers out on the internet are still signaling the old key, and I've taken care of one problem. One very important aspect of that, this is one user behind one address, right? So if other resolvers have 300,000 users behind them, it's not, even though the really dark bad line dropped by a huge amount, it's not reflective of potentially the number of users I've helped, because there was a one-to-one mapping between IP addresses and users. So that was really hard. So looking into what other people have done, a couple of other people much more recently, Warren Kamari, did a search for the old key in the GitHub interface and found that there was 2,069 references to the old key and only 412 of the new one. I did a Google search, sort of similar things. There's more references to the old SHA-256, hash than the newer one. Roy Ahrens has recently, in ICANN's Octo team, has looked into how serious are some of these and has found a lot of commonality. And GitHub has forks and all that kind of stuff, and how many of those code bases are new and being used. That analysis is not entirely finished yet, although he gave a presentation at IEPG, I think, on Sunday that I both missed and didn't copy his slides into this one because they were already due. So there's lots of stuff going on. So let's talk about lessons learned. Like what can we learn about this in the first place? So first off, flag days are hard. You'd think that we would know that within the IETF by now. But within DNSSEC, because of packet size constraints, we can't do double signatures that easily. So ICANN's plan for rolling the key involved directly switching the key on a single day and not doing double signing for a while to let old and new users kind of migrate. So that's hard to do. And more importantly for me, I tracked down only a small fraction of the actual traffic that was out there sending keys. In fact, BRU is still receiving 12% of its traffic from addresses only signaling the old key. And tracking down misuse in over 1 million possible sources sending stuff to you is very, very hard. And I only solved a very small piece of the pie, as I mentioned. But why is it that rolling TAs for DNSSEC is so hard? Well, a couple of things. The 8145 queries are actually hard signals. They are decoupled from the query of looking for the actual key, right? So a resolver might send a query saying, hey, I need your keys, and then in a totally separate key that's not bound, send a query for I'm using this key. And those two queries can go to different places, so you can't even correlate them. As well as there's no indication of intent. You may just be, hey, I have these keys and I'm sending these, I need these keys, but there's no indication that I'm gonna use the keys to actually do validation. So that's really what my recommendation is for the future. When you're thinking about designing, internet protocols and things like that, include signaling within it, include sort of this intent mechanism, and then think about how software updates and how configuration updates happen over time. It's not easy, and trust anchor keys are rather critical bootstrapping issues. So you really need to design for automatic updates from day one. Unfortunately, the DNSSEC automatic update, mechanism, which is defined by 5011, came after the rest of the DNSSEC system was designed. And doing it afterward is challenging because software updates slowly. So if you don't have everything going out on day one, you now have all these systems deployed that understand the cryptography but don't know how to update their base keys. And then also select update frequencies wisely. And there's really sort of two choices, and this is sort of a hint for a future presentation to come where I'm studying a bunch of systems. You have a choice of doing it really frequently so that everybody gets used to the fact that it's updating. Let's Encrypt, for example, makes you update their keys to your web servers on a 3-month basis. You get used to it. You either have to automate it or you fail. Or you have to do it sort of rarely and expect that hard things are going to break, and that you better use really strong, well-protected keys. You better have widely overlapping signatures and things like that. So as security is being used more and more in IETF protocols, you really need to think about what happens 20 years down the line, what happens 10 years down the line when people need to update their keys. So any questions? We were last in London, so this is a nice picture from London, although ironically not from the last IETF, but from the London before that, while Roy walks to the microphone.
Roy Arends from ICANN, the Octo team you just mentioned. First off, there's another blob of data coming your way. You've asked for this last week, and it was a bit busy this week, but it's coming your way.
I appreciate that.
You mentioned flag days are hard, which is correct. But also in that same context you mentioned, doing double signatures might solve something. The problem is not that we sign with the new key. The problem is that we stop signing with the old key.
Yes.
And even if you do double signatures, at one point we need to stop signing with the old key.
Yes.
So doing double signatures wouldn't really have solved anything. We would have that same. There would be more overlap, sure, but
yeah,
you would still have that problem.
And you're absolutely right. At some point, you have to turn off using the old key.
Yes. You mentioned the GitHub research. There's an enormous amount of craft, dead bodies on GitHub. We've seen, I can give you a nice example. Part of the 2000 that you saw, these are 2000 files, not 2000 repositories.
Correct.
So there are 1100 repositories, but in the end, there are 300 unique files on GitHub. So these are distinctly different from each other. The 300 are in the long tail. In the short tail, there is, as an example, DNSSEC_chain_validator.cc, which is in a very popular repository, Chromium. However, this was taken out of Chromium about 6 years ago. And so, but these things get copied and forked and cloned on GitHub, so there's a lot of stuff of that. OpenWRT is another example. OpenWRT is what you see. OpenWRT, you can download that, install it, and then you can get a config overlay from GitHub. And you see a lot of old keys in there. What you also see a lot, as in all of them, they have DNSSEC disabled by default. Now, of course, what people do after you install it and download the configuration, we don't know what people do after that. They might enable DNSSEC, and they might have a problem. But yeah, good work. Hopefully you find more stuff. And,
well, the point of this talk is more, what we should do within the IETF and lessons learned. But yes.
Okay, perfect. Thank you.
Thank you.
Davey?
Hi, Davey.
Hello, Wes. Thank you for your presentation, for the measurements, and also I have a feeling that maybe people are only aware of the announcement that I can delay the KSK row, but not aware that tons of work to be done behind. So really thank you for the sharing. And I come up with two ideas. One is that I heard that there is a working group or research group called SUIT. I just heard it yesterday, and it's about the update of the IoT devices. I think it's a similar problem that DNS currently, the software, there's no updates or protocol to support to compliance with the protocol, right? Or rover as a case. So I'm thinking about if there any maybe potential work can be done or any discussion already happened.
Yeah, I mean, I think, the Internet of Things issue is much wider than DNS, right? They have how many trust anchor bootstrapping issues do they have? And the fact that users don't update firmware, for example, once they buy a little modem, and if we don't get automatic updates and turned on for that, how are they going to eventually get new HTTPS certificates or whatever protocols they're making use of, management protocols or anything? That has to be dealt with. It's not just a DNS specific problem, especially for those widely deployed very small devices.
Okay. The second idea is that I once proposed a small draft on the KSK role team, and about the comparison and analyze of how the rover is so difficult, because I compare the transition process compared to IPv6 transition and HTTPS transition, and I found that there is no such transition period for the KSK role. We just choose a flag day and to stop signing. So that will trouble. That's the case. That's the reason I think, in my mind, the best, the most key difference between the different technology change. So I'm propose a very intuitive idea, and I think maybe after the KSK rover performed in this year, the August, right? October. I think there are more challenge work when people think about the algorithm role, because maybe the capability to roll the algorithm may be more difficult for the key. So I'm still thinking about maybe some dual stack or backward compatible way of key role or algorithm role can be developed later. I ask you if you have any.
No, I mean, I appreciate the question, and in particular, I mean, Roy is 100% right that at some point you have to remove the old key, so double signatures don't help you. The one thing that it does help is it allows you to have a longer extension where you publish a newer key, which we've already done, right, with this. And so I would argue that the biggest lesson learned for me was that the 3-month window last year from July to October was too short. And that we really needed a longer window, both for measurement and analysis, as well as to make sure that validators out in the world really did get updated. Sometimes there are some slow rollout paths. Now that it's been a year and a month, well, I don't think, it would have been nice if we could double sign for a year so that rollout could continue, and yet we could use the new key. But, that there is some thinking that needs to be done after the key roll really finishes in next year, when the old key is actually removed and signed as revoked. But thanks for your question.
Okay, thank you.
All right.
Okay, thank you very much. That's the end of the session. I forgot to mention that Magnus was so kind and scribed today, and there was a little bit more discussion than usually, so it was actually an effort. But thank you so much for having the discussion here. That was great. And then see you next time. So it's like, I'm not sure. So actually, I don't think in our groups. No, in the group of my profession, I don't think we have but I also don't know.